So good morning, everybody, and welcome to today's session on strong interactions on Hadron physics. So my name is Carlos Muñoz, and I'll be chairing the first part of the session. So we have a full agenda, and I would really ask the speakers to keep the time allocated, which is 12 minutes, to allow a few minutes of questions at the end of their talks. If you have questions during a presentation, please raise your hand using the raise hand button in the Zoom app, and I'll call your name at the end of the talk so you can ask your question. So without further ado, let's start our first presentation, which is by Christophe Coutard. Christophe, please go ahead.
Good morning. So I will start to share my screen.
We can see it.
Yeah, okay, good. So I will go to presentation mode. Okay, so thank you very much for giving me an opportunity to give the talk. So this is a talk based on papers written together with those people. Okay, I cannot go to next slide for some reason. Oh, sorry. Okay, now it's fine. So the KT. So first, I'm going to discuss just KT factorization. So the KT factorization is a framework where already at leading order gives you access to the full phase space. So similarly to collinear factorization, you have a hard matrix element and parton density function, which now depend on the transversal momentum. So this hard matrix element here, you calculate it with off-shell initial state partons, which carry some transversal momentum. And as I said, the parton densities used here depend on transversal momentum too. So to see this, this is the diagram which shows, incoming partons in the collinear factorization have to be back-to-back because of the momentum conservation. In the KT factorization, it is not necessary because the incoming momenta can be off-shell, so you have access to the full phase space in the end. So the final state partons can be just at any azimuthal angle. Okay, and here is the basic, delta phi distribution of dijets, which shows you that you you can have the full distribution across the all values of delta phi. And in standard collinear factorization, you will have a delta function just here at delta phi equal pi. Okay. So to calculate matrix elements, it's kind of the basic idea is very simple. So you have just draw your Feynman diagrams, and for the off-shell initial state gluon, you just apply certain polarization sum, which kind of tells you that the incoming parton is off-shell. And so this is the basic, the idea is that the off-shellness in principle comes from some auxiliary parton, which gives this KT to this gluon, and then it becomes off-shell. However, to go to more complex calculations, one needs to develop a method which allows you to calculate any process at this moment at tree level, or although we have also results, preliminary results for NLO. So the idea is to use the framework of collinear factorization and to embed the KT dependent matrix element in a larger process, which actually puts this initial partons offshore. And then by observing that one needs to have all this kind of contributions to have gauge invariance, one takes certain limit, and this is the method which allows you to calculate actually any tree-level matrix elements in this KT factorization. So this is in agreement with Lipatov effective action, who derived from QCD methods to calculate such off-shell diagrams. And then there is also some more formal derivation by Piotr Kotko based on gauge links, which is actually, gauge link is just such a line and which also keeps the gauge invariance of the off-shell matrix element. Yeah. And this, all these things is implemented in a Monte Carlo event generator called KT. It's available on the web. It's written by Andreas van Hammeren. So now the next step is the parton shower. So if you have this off-shell matrix element, one can do many processes without using parton shower. But if you want to really look at the details of all produced final states and put some additional cards, etc., and constraints, you need Monte Carlo. So then there is a Monte Carlo for TMD parton densities. It's there were already talks by Bermudez, Martinez, and Taheri on this. So I will be brief, but the basic idea is that emission of such gluons allow you to, and keeping the exact kinematics, allow you to construct TMD parton density. And this construction works for all flavors and gluons. So in principle, there is a full framework for matrix elements and Monte Carlo working on this within this KT factorization. However, there is one shortcoming here, that the splitting functions are still collinear. And so the KT is generated only via transversal, via momentum conservation. So here are the plots of the gluon densities that were obtained within this Monte Carlo parton branching Monte Carlo. So this is just to illustrate that it works, gives gluon densities and also some yeah. Okay, so here is some application of this framework. So for instance, I'm showing now Z and jet production. So this is a PT of Z, where we compared the calculations with existing Monte Carlo generators. And we see that in particular, we can demonstrate that in the low PT region, for instance, there is there's a contribution of MPI effects, which is taken into account in PAUHEC, but we don't take into account. However, our calculation is purely based on this TMD physics, and and it's a kind of a three-level calculation, but it's already I would say reasonable. Okay, so here is application to dye-jet production in central rapidity region. So this is so here we just compare the calculation, just parton densities and matrix elements. This is this line. The blue line is matrix element parton densities, and on top of this we take into account shower, fine initial state shower, which shows that this such contributions from shower is relevant at smaller values of delta phi. Okay, now application to production of trijets in more forward rapidity region. The parton level calculation is just this black continuous line. However, if you want to, then we compare also just matrix elements convoluted with parton densities, and then we actually in this case for trijets we are on top of this parton level calculation. So it seems that in this case, for higher multiplicity, shower is actually affects the distribution less. So the kinematic is already better described, better accounted for more multiplicity finite state. So this method has been also applied to construct parton densities for lead to be able to calculate observables for P lead at LHC. So the idea is to take some initial condition from collinear gluon densities and to evolve it using the parton shower, parton branching method. And you
Christoph,
yes?
You have 1 minute left.
Okay.
Thank you.
And so those are our results for distribution of Drell-Yan pairs in PLED. So you see that we are at the 3 level, but we describe the PT distribution in another, and it's very good description. Yeah. So here are the preliminary results for electron-ion collider. So here the final state is electron and pair of jets. So this is the distribution that we get. Here we compare some nonlinear equations versus linear equations, and we see that this process is insensitive for this, let's say, saturation effects, which you can expect. So here is the basic thing about saturation. If you go to lower and lower x, the gluons start to recombine, and actually you need to change your factorization scheme from the simple one which I presented before. We have more complicated, where these things here are just take into account the nonlinearity, but the structure, overall structure is the same. Okay, and here are some results for the saturation for proton lead at LHC. We compare this framework, which was on 2 slides before, against the proton lead data and proton data as measured by Atlas. And we describe shapes of this distribution very well. And this is to describe this, saturation is necessary, and also some other effects like the initial state shower effect, called also Sudakov form factor. So here is my summary. Yeah, so I will just, maybe you can just have a look, read it, because I don't want to take more time. Thank you.
I don't hear the chairs, but can I ask a question while we're waiting?
Yeah, sure.
Okay, thanks. You can hear me. Okay. So I was wondering about your slide with the ZPT, where you were comparing to the POWEC predictions. And we're mentioning that this very low PT region is dominated by MPI contributions, or is affected by MPI contributions. Did you check this by enabling and disabling MPI in the shower? Because I would be surprised to see such a big contribution there. But
yes, I mean we just this was checked.
Okay.
Yes.
Thanks.
Sorry, thank you. Can you hear me now? I was actually talking but muted. I apologize for that.
Yes, we can hear you now.
Okay, so so are there any other questions for Christoph? Okay, if not, let's move to the next presentation, which will be by Frank Seeger on measurements of prompt photon production with Atlas. Frank, please go ahead.
Yes, so let me know if you can hear me and see my slides.
Yes, we can do both.
Okay, very good. Then I'll get started.
Yes.
Thanks. Yeah, it's a pleasure to present the latest measurements of prompt photon production on behalf of the Atlas collaboration today. And I get started right away and start with one plot which people typically associate to this phrase of prompt photon production in Atlas, namely the left-hand plot, where we use photons, the photon process merely as a, or the photons merely as a tool to discover actually another process, namely resonances like the Higgs boson in this case here, or also as a tool for things like jet calibrations or PDF fits using the photon data. But today I actually want to talk about the prompt photon processes, excuse me, talk about the prompt photon processes themselves, because they are actually quite an interesting process in terms of testing for perturbative QCD. And that is even despite they are such a simple, apparently QED core process. So we'll see later in my talk that this is actually quite interesting for QCD. That's why it's in this session. Now, if we're talking about prompt photons at the LHC, there are different sources of such photons. And the one which is the most abundant by far is the one on the right-hand side, which are actually the ones that we're not interested in, namely non-prompt photons, which come from hadron decays like the pi naught. And they're actually the main background for the searches, or for the measurements that I'm going to present today. So we'll see those later in a little bit. And the other one on the other side of the page we've already seen is the resonant production of photon pairs. And those are, of course, part of the prompt photon measurements that I'm going to show today, but they're completely negligible in the phase spaces that we're looking at. So if you're actually interested in those, I'll invite you to look at the dedicated Atlas searches or measurements presented by other people at this conference. So that leaves us with the middle of this whole slide, namely the continuum production of photon pairs, which on the theory side is typically described by direct production of photons and matrix elements, or fragmentation production in fragmentation functions and parton showers, and experimentally is accessible by looking for isolated photons, isolated from hadronic activity, and with a strict identification of the photon within the EM shower shape. So those are the ones that we want to look at, and Atlas actually has a very active prompt photon measurement program, and I've tried to give an overview by dividing it into this landscape of the number of photons involved in the measurement and the number of jets involved. And of course, it starts with the single photon measurements on the left-hand column, where we have lots of inclusive photon measurements at the various center of mass energies, photon plus one jet measurements, and also photon plus two or more jet measurements in this case. Then going further on the x-axis to the right, we also have a diphoton measurement at various center of mass energies, and actually one of them being brand new, public today and shown for the first time. So we'll go into a bit more detail on that. And last but not least, we also have 3 photon measurements at ATV in the Atlas measurement program. So clearly this is too much to talk about in 12 minutes today. So I'll focus on the most recent measurements, namely the single photon plus 2 jet measurement shown above here, and the new diphoton measurement in 13 TeV just released today. So let's look at the analysis definitions first of those 2 measurements. The definition of the fiducial phase space, I've put it here up as tables, but don't expect you to look into all the details of this table. Let me just point out that one main difference is that the single photon measurement is using a very hard photon requirement of 150 GeV of PT, while the diphoton measurement is relatively soft with 40 or 30 GeV, which makes a bit of a difference. The different observables are constructed from these from these final states, and I'll show a few results of those in a minute. But before we actually go to the results, we have to talk about the difficult parts of the analysis. And one of the main difficult part is estimating this background from the jets misidentified as photons that we saw earlier, where the photons are actually coming just from a pi naught. And the problem is that our simulation is not working very well to model this kind of background. So we can't just subtract it using Monte Carlo, but we have to estimate it in a data-driven approach using background-enriched control regions, typically based on the a loosened identification and isolation cut, as shown here on the top right, those two variables being the ones that identify our signal. And there's the basic idea here, and that is also the one that is used for the single photon analysis, is this ABCD sideband technique, where you basically assume that if you know the ratio between D and C and D and B as background between those background control regions, if you know the ratio of the background between those and the two variables are uncorrelated, the isolation and the identification, then you can directly get your background prediction in the signal region A from those measurements. And then you correct for it a little bit with a correlation factor R that takes into account the correlation between isolation and identification. This was applied for the single photon analysis, while for the diphoton analysis, it's a bit more complicated. Obviously, we have to extend this to the case of two photons now. So we have two photons times two identification or isolation variable. So this is basically 4D. So we don't have just 4 regions, A, B, C, D, but actually 16 regions in our fit now, with one of them being the signal region and 15 background control regions. And we also have more processes that can contribute to the background. So we can have the case where, besides the signal, of course, just one of the photons is produced by a jet or faked by a jet, or both of them are faked by a jet. So this is fed into a likelihood fit, and then comes out a plot like the one on the right-hand side for each observable bin, where you see the decomposition of the different processes in each of the bins, and then a lot of signal in the signal region, of course. All right, so once we've identified this main background, then I also just want to touch briefly upon the sub-leading backgrounds in the diphoton case, where one of them is basically photons faked by or radiated off electrons. And that is, as expected, just relevant in certain regions, namely where the Trajan process is relevant around M gamma gamma, or MEE in this case, close to the Z mass. So you can see this magenta background here popping up around 90 GeV. And then another even smaller background, just 1% inclusively, that is very interesting because it stems from 2 single photon events coming from different pile-up interactions, so from different vertices. And while this is small inclusively, it actually becomes significant in some regions, like the cosine theta star going towards 1 region, which is kind of a decorrelated configuration. So this is actually interesting to get this shape also correct, and the normalization, of course. So this is done in a sophisticated data-driven estimation, which there's a slide in the backup in case you're interested, we can discuss later. All right, now that we've the backgrounds under control, let's see what the uncertainties are, the main uncertainties in the two analyses. In the single photon case, we're dominated by the jet and photon energy scale uncertainties. So in green here, the jet energy scale, and in red, the photon energy scale uncertainty, which becomes large at high photon transverse energy. Maybe noteworthy is that the background fit uncertainty is not large here, related to this main background I was talking about, because at this high transverse mass, transverse energy of the photons, we have a very high signal purity. So with these uncertainties propagated to the results, we can look at the first results from the single photon plus 2 jet analysis here. I flashed the fiducial region earlier, and you might have seen that the phase space was divided into 3 different regions. This total, fragmentation enriched, and direct enriched regions, and I'm showing here one observable from each of the regions, and it's actually quite nice to be able to do this division to be more sensitive to fragmentation components in the measurement. The description by the Monte Carlos used here is fair. There are some problems there, the known high MJJ mismodeling, or the Pythia Parton-Chow not being able to describe the PT shapes very well, but this is kind of also expected. So let's go to the diphoton analysis. The dominant uncertainties here are not actually the photon energy scale, but actually coming from the background estimation and from the modeling of the photon isolation variable. The others are subleading, which is different from the single photon analysis, as I mentioned earlier, simply because of the lower PT cuts of the photons here. In total, we have an integrated uncertainty of around 8%, which becomes larger in certain regions of phase space, like the low invariant mass region, where we go up to 25%. But we have to keep in mind that this is the first measurement in this region. So the low purity, so high background rate, and the low data statistics in this multi-jet dominated region is causing this large background estimation uncertainty. Now, with the uncertainties out of the way, we can go straight for the results, which are, as I said, brand new. We see an actually impressive impact from perturbative QCD, even on the simple QED process, even on the inclusive rate, as you can see on the right-hand top plot. And also in the bottom for the different predictions that I've listed here at either fixed order next to leading order with fragmentation from Difox, or next to leading order from an NLO-jet, or a NLO merged Monte Carlo prediction from Sherpa. Actually, the perturbative regions are generally modeled very well by the most precise predictions, while in some of the soft collinear regions here, for example, at low PT gamma gamma, of course, the fixed order predictions are not expected to be valid. So we have here the leading and subleading photon PT as a distribution, and the PT of the diphoton system. And going on to the next slide, we have two more observables, namely one being the invariant mass of the diphoton system, which is actually got quite an interesting shape, which is sculpted by the PT cuts. And the region below the peak is populated through multi-jet configurations. So those are, of course, challenging to model. And this whole distribution is just best modeled by these higher order predictions. And in this low mass region, even just still barely within uncertainties. On the right-hand side, we see the scattering angle with respect to the beam axis in this special frame, Collins-Soper frame, which shows this somewhat interesting behavior towards the value of 1, which is sensitive to uncorrelated photons, which can, for example, be uncorrelated by multiple jets being present in association with them, which is apparently described better here in this in the Sherpa Monte Carlo description. And last but not least, three more observers, three more variables which are more sensitive to this back-to-back configuration, which is sensitive to soft and collinear emissions. So at fixed order, you would not expect these regions here always on the left-hand side to be modeled very well because they would need resummation. A merged approach with the parton shower is modeling those quite well in all three cases. The regions with the large decorrelation, on the other hand, are modeled well with the highest precision predictions, whereas the NLO prediction is struggling as effectively for these observables, it's only leading order accurate, so it's not too unexpected. All right, that brings me to my conclusions. I hope you agree that prompt photons are a pillar of the LHC physics program, and not just because of the Higgs discovery in the diphoton case, but because of the prompt photon measurements themselves. I've presented you two measurements today, one in single photon plus 2-jet production, and one in the diphoton production at 13 TeV with the full run 2 data, and we found impressive effects from the strong interaction on this simple QED process. Thank you very much for your attention. I'm happy to answer any questions you might have.
Thank you, Frank. Are there any questions? Yes, Miroslav.
Hi, Mira. On the previous slide, 21, I guess, I didn't get what's the small zoomed plot?
Sorry, yes, I should have said this. So there's a logarithmic plot. So both logarithmic in x-axis and y-axis is the main plot. And then there's just a linear inset plot, which is showing the region around the x value being at 0 a bit more closely, so that you can see this this resummation behavior.
Oh, thanks.
Sorry, yes. There's also a note released today, which is linked here in the conclusion slide, where you can see these plots a bit more in higher resolution and with more explanation.
Any other questions for our speaker? Okay, if not, thank you again. And let's move off to our next talk, which will be by Jarek van Onsel, who will be telling us about Monte Carlo modeling and tuning in CMS. Jarek,
thank you. I will
please
share.
go ahead.
Can you see the slides?
Yes, please go ahead.
Yeah, so I will present the Monte Carlo modeling and tuning in CMS. In a Hadron collision, there is a wide range of different features that needs to be simulated by Monte Carlo generators. These include hard scattering matrix elements, the parton showers and radiation, and the hadronization and hadron decays. There may also be additional interactions taking place in a collision referred to as multiple parton interactions, MPI. And furthermore, the remnants of the proton also still undergo interactions and hadronization. And the combination of MPI and beam remnants is typically referred to as underlying event. The partons in the event exchange color, and the rearrangement of these color fields in the simulation is what we refer to as color reconnection. So in CMS, we commonly use Monte Carlo generators such as POWHEG and MATGRAPH for both for fixed order matrix element calculations. Sherpa, which is a multi-purpose generator, just like Pitya and Herwig, but these last two are often used to interface parton shower and underlying event simulation to the matrix element. The underlying event, the parton shower development and hadronization typically involve lower energy scales, which means that these aspects are not always calculable in perturbative QCD. Therefore, their modeling is governed by phenomenological parameters that can be tuned to observe the data. And CMS performed such a tuning for the Pitya 8 generator and more recently for the Herwig 7 generator for the MPI and color reconnection parameters in these tables. We consider a PT threshold, PT0, that governs the transition between soft and hard interactions. The lower this threshold, the more MPI are generated, meaning more underlying event activity. This parameter has an energy dependence depends on the center of mass energy, which is parameterized by an exponential function. Next, there are parameters related to the overlap distribution between the two colliding protons. Generally, a larger or denser overlap means more MPI. And finally, we consider parameters related to the color reconnection probability. A large value increases the amount of color reconnection and tends to reduce the final particle multiplicities. An important remark is that the parton distribution functions and the strong coupling alpha S also enter these parts of the simulation and therefore affect the predictions. And technically, the tuning is performed by fitting predictions to data using the Rivet and Professor frameworks. More specifically, this involves minimizing a chi-square distribution, a chi-square function with respect to the tuning parameters using the measured and observed bin contents. The tunes are extracted from relevant sensitive observables measured in minimum bias data. The observables include the charged particle multiplicity and scalar PT sum densities as function of the PT of the leading track or leading charged particle jet. These are measured in the transverse regions, and as illustrated in this sketch, one can define a transmax and transmin region depending on where the most charged particles or highest scalar PT sum is located. Another observable used in the tuning is the charged particle multiplicity as a function of the pseudo-rapidity. And these data are recorded at various energies by the CMS and CDF detectors. Components of the hard scattering, such as hadronization and ISR, FSR, may affect these underlying event observables. For instance, the transmax region is more sensitive to ISR and FSR, while transmin more to MPI and beam remnants. And predictions for the distributions of the observables are obtained by simulating non-diffractive and diffractive inelastic events for each choice of tune parameters. So these are the results for 5 CMS PTA tunes labeled as CP1 to 5. In these tunes, different assumptions are made for the order of the PDF set and the alpha S value and running. We typically use higher order PDFs in the NLO matrix element, so this may motivate the usage of higher order PDFs in the Parton shower and underlying event. But in any case, the different assumptions in the CP tunes allow us to check the consistency of matching the order of PDFs in the matrix element and tunes. CP1 and CP2 can be seen as LO PDF tunes, the alpha S value. So yeah, while CP3 is a NLO PDF tune, and CP4 and CP5 an NLO PDF tunes, where CP5 just differs from CP4 by the enabled rapidity ordering of ISR. In these higher order PDF tunes, the alpha S value is chosen lower to be consistent with the NLO calculation. There are significant differences mainly between leading order and higher order PDF-based tunes in the values of PT0 and its energy dependence, as well as the amount of color reconnection. And these differences can be explained by the different shapes of gluon densities at small x in the assumed PDFs, as well as the assumed alpha S running. So these are example distributions of observables in the transmin region used in the PTA 8 tuning. In the upper row, the LO PDF tunes, and in the lower row, the higher order PDF tunes. At the left, the charged particle multiplicity density, and at the right, the PT sum density. The rising part of the spectrum, where diffraction processes become more important, is not always well described, but we should note that, in fact, in this very low region below 3 GeV, we don't include this in the tuning. The different tunes all describe the minimum bias and underlying event observables that we studied in a similar way. We have performed many validations of the PTA tunes because ideally we would like an underlying event tune to be universal and describe a wide range of processes and observables. Event shape observables measured at lab are of interest because due to the leptonic initial state, these observables are particularly sensitive to the alpha S value assumed in FSR. The so-called thrust observable T is shown here, where higher values of T means that the event is more dijet-like and lower values more isotropic. And we observed that the tunes assuming a lower value of alpha S, resulting in less isotropic events, describe the data better. In multi-jet events, we looked, for instance, at angular separation between the two leading jets shown at the left, where the predictions are obtained from NLO dijet matrix elements from POWHEC merged with PTA 8. We see that tunes based on NLO alpha S running are better than tunes with LO running, since the former results in a lower amount of FSR and thus less jet decorrelation. Validations were also performed using top quark pair events, as shown at the right, for the number of additional jets in the event, where the predictions are obtained from interfacing NLO matrix elements from POWHEC with PTA 8. And we see there that an NLO alpha S value and an ISR rapidity ordering switched on, as assumed in the CP5 tune, is favored in these calculations. Moving on to the results of the Rubik 7 tuning, we note that here different assumptions are made in the underlying event only for the order of the PDF set and the alpha S value and running. CH1 is a tune where an NLO PDF is assumed in the underlying event, which is changed to a leading order PDF in CH2. And then CH3 has the same assumptions as CH2, but but just the alpha S value is chosen to be higher and matching the leading order. In all these CH tunes, an low PDF in the Parton shower is assumed consistent with the PDF we typically use in matrix element calculations. Soft tune in this table refers to default tune performed by the Hurwicz 7 authors using Atlas data. We see that the CH tunes have a lower PT0 and energy exponent compared to soft tune, which generally leads to an increased amount of MPI in these tunes. And from the chi-square values, we can deduce that generally a leading order PDF for the underlying event, as assumed in CH2 and CH3, is preferred. But the choice of alpha S in the PDF seems less important. So these are some example observables used in the Hurwicz 7 tuning. So at the left, you can see the charged particle multiplicity as a function of the pseudo-rapidity, where it is apparent that in the CH tunes there is an increased amount of MPI compared to soft tune. And at the right, the charged PT sum density is shown in the transmin region. And the CH tunes show typically good agreement in the plateau of such spectra, but again, there are some discrepancies in the rising part of the spectrum, which was not included in the tuning. And we performed again various validations in different processes and observables. So the left figure shows a distribution of the PT of the hadronic top quark in top quark pair events, again with an NLO matrix element calculation using PowHack interfaced with Hurwicz 7. Generally, kinematic distributions in top quark pair events are well described, but as one sees in the right figure, the CH tunes tend to underestimate a bit the ICHEP multiplicity, but there the scale uncertainties are expected to be higher. In vector boson production, where predictions are obtained from NLO matrix element calculations using MatGraph, we checked, for instance, the exclusive chat multiplicity at the left, and we observe a similarly good description by all tunes. And we also looked at the underlying event observables in Z plus jets production, such as the charged PT sum density at the right, as a function of the PT of the dimuon system. This observable is sensitive to the underlying event description at higher scales than minimum bias data. And we see that the CH tunes describe the data well. So to summarize, CMS extracted and validated sets of tunes for the underlying event simulation. For Pythia 8, it was observed that the new tunes improve on older tunes that were extracted at lower center of mass energy. And for the first time, predictions based on higher order PDFs were shown to give a reliable description. In particular, the CP5 tune provides a good overall description, and this is the tune that is most used in CMS. We also derived the first Hurwicz 7 tunes with CMS data, and they provide a good overall description, and the CH3 tune is the one that will be used in CMS. And we also found that in general, the underlying event simulation from the new tunes interfaced with higher order and multi-leg matrix elements still provide a good description. And the extracted tunes and uncertainties are now widely used in the Run2 CMS measurements and searches. Thank you.
Thank you very much. Are there questions? I don't see any raised hands. So let me ask, you referred to universality. I mean, and what's your opinion on the current status of these generators? I mean, are they universal enough, or do you think it's when they don't reproduce some of the channels, is it a matter of tuning, or is it some physics that should be implemented that it's not there yet?
Yeah, I think they're reasonably universal. I mean, the things we see in the validations across many processes and final states looks at least very good. But of course, there are a few cases where it seems that, for example, other tunes describe the data better than than in other regions. So one can wonder why in some cases, for example, CP2 might describe a bit better the data than CP5. So in that sense, it's not as universal as it probably could be, but I think it's definitely on the good way.
Okay, thank you. Any other questions? If not, let's thank Eric again. Move to our next presentation, which will be by Miroslav Miska. Please go ahead. We can already see your screen.
Yes, hi.
We don't see your screen anymore.
Yes.
Oh, no, it's coming. Okay, very good.
So I would like to shortly describe how we implemented space-time coordinates of partons inside the PP collision modeling by Herrick 7, and how we used it for implement a new way of color reconnection. As we just had to talk about tuning, so probably everybody knows what the Herrick 7 is. So just want to point out its general purpose Monte Carlo. So it calculates, it provides you all the particles in the final state in the PP collision, not only just products of the hard process of interest. And since the reality of MPI, the simultaneous interaction of several pairs of partons within one PP collision is modeled, there are actually many of them. And there's high uncertainty how to connect them in color lines in the color space. So there's one kind of artificial step coming in, which is called color reconnection, and this is what I will talk about. So far, all the calculation is done actually in the energy momentum framework. It deals with the four momenta of the particles, but we completely lack the information how far in spatial the partons are. And that's what we wanted to use for color reconnection, because color importance of this step, this algorithm rises. For instance, top quark mass measurement reported like 10% uncertainty coming from the color reconnection. And another motivation is also like for larger systems like heavy ion collision, that would be highly important to have this information, how large the area is, where the parton actually is. Yes, for losing energy, some particle traveling through the QGP and so on. And Herrick 7 is not alone. Also, PTA pursues this direction. Also, there is a brand new paper you can have a look at. So, since the motivation started with MPI, let me say a few words about it. Herrick first generates samples number of how many MPIs will produce. And for this, because it's governed by Poisson distribution, it needs the mean number. And with the given impact parameter of the collision, it is calculated through the already mentioned overlap function times inclusive cross-section. Herwig models this overlap function as a Bessel function of third kind, which is the result of this electromagnetic form factor for the transfer distribution, this G function. And here I want to point out there is this parameter mu squared, also already mentioned, as meaning of inverse proton radius squared. And you can see the overlap shape for several mu square values. So the larger it is, the smaller the overlap actually is and more dense, let's say. So this is one parameter. The story goes a bit more complicated because you need to actually distinguish which MPI are hard enough to calculate perturbatively and which needs to be modeled phenomenologically. So we have a cutoff PT min, which is also somehow extrapolated from some basic value, which is tunable parameter. So these parameters comes from modeling of MPI itself. What is new? What we did? We focused on transverse plane, XY plane, so perpendicular to the beam line. And we assume that MPIs can actually interact in several positions in this space. So what we needed is the actual impact parameter of the collision, of the given collision we just calculate. So the logic is a bit inverse. So Herwig first samples how many interactions, hard and soft, it produces, and then we use it for actually getting the impact parameter of the collision. And this is how we kind of in the looping algorithm decide where the position of MPIs might be inside this overlap region. And we have several models like the Bessel function I mentioned, but we also tried Bladdick disk and Gaussian. And the second source of displacement patterns can also be their evolution. This is quite old story. You can see the paper from Bifia people, 40 years old. And also code in Herwig 7 is inherited from Fortran version. So the model is that parton can travel according to its proper time, which is governed by some random sampling for the exponential law. And there is parameter mean lifetime. And this is as a function of its virtuality of the parton. Right? Roughly speaking, it's 1 over root square of virtuality. And this is what we observe, that inside actually the shower evolution of the parton, so the first step don't really allow parton to travel anywhere. If you look at the left plot, it's example event. So the black lines inside, you can see hardly, but there is. That's how far partons, any parton can travel inside the shower. And the red lines are the very final step in the shower where the virtuality is the lowest. So it's kind of last step jump, let's say. It can be even 3 Fermis, as you can see. Statistically speaking, there's the right plot, just focus for the red solid line, for instance. This is percentage, how far in the entire distance traveled by all partons, all particles, is these jumps last step shower partons. So it's almost 100%, like 95% in all peaks. So we were playing with these virtualities, how to truncate, how to cut it off. It's 1, 2, 5G, and so on. If you would be curious about the green line, because Higgs can travel very far, so the distribution is different for Higgs. So after playing with these virtualities, we actually decided that all partons in this final step of shower will be assigned the same virtuality. We call it minimum virtuality ni, and we made it tunable parameter. So we actually decided to ignore all the shower except the last jump. And this would produce the example event. You can see on the left, and there are these 4 circles. It's 4 MPIs in the event with their center, and around this center you have partons which evolve from the center. So we have green partons from 1 MPI, red from 2nd, and so on. So you can see in the transfer space how it might look like. So now the color recognition comes in. Herwig uses cluster algorithm. So it creates in the default version or the original version like mesonic clusters. So quark, anti-quark creates a cluster, colorless object. But we can also assume that such partons can exchange very soft gluon and swap the color. So the upper plot is the same event, but the upper plot creates different clusters than the lower plot. And there are many, many ways how to do it. You can have a look at the papers several motivations how to do it. What we pursued is called baryonic color reconnection. If you focus on the cluster A, there's a quark and anti-quark. Quark is white and anti-quark is black. So in the rest frame of this cluster, they fly away each other, and we loop over other clusters. And if it's look like in the top plot, top picture, that along the first anti-quark flies quark, we may want to connect them into a cluster C and the other to cluster D. So this would be like mesonic color connection. But it can also happen that this white upper circle would be black. So we would like to say, okay, if there are another black, like in the left bottom picture, we would find 3 clusters aligned in the rapidity like that. We may create actually so-called baryonic clusters created by 3 quarks or 3 anti-quarks. And of course, we need 2 things, some tunable probability, if to do it, if to reconnect or not, and of course some measure, like to decide what kind of reconnection we prefer, right? And this is, again, new step. This measure R squared is now combination of delta Y, the rapidity difference, and delta R, that's the distance of the partons in the transfer space. And here comes another tunable parameter, D0. I can call it like characteristic length. And it actually scales which of these 2 components of the measure are, let's say, more important for the color reconnection. So here finally comes some result. There are many parameters. I didn't cover all of them, but the new ones, the minimum virtuality assigned for last step, parton shower gluons is the x-axis in the chi-square plot, and the best value was found quite large, 4.5 G squared, and the characteristic length D0 is 0.15 Fermi. Right? We also show 2 variations, like we decided to take it to show variability of the model, flexibility. We tuned the model on the Atlas CMS and some ALICE data for minimum bias and underlying event. So just a taste of the results. So it's a rapidity of the charged particles for 5 event selections. You can see, for instance, in the upper line, that the red line of the best tune sits on the data quite well. So that's the actually main result, that we did not really jump somewhere away of data, that the model would completely destroy the success of the Herwig. There is, for instance, transverse momenta of the charged particles, also against the minimum bias Atlas data. So this is like flagship results. So some modeling is very well, some modeling is, of course, not that well, like PT of the leading track. But this modeling, you see, it's actually related to Herwig itself. It's a known feature, not really unsuccess of the new color reconnection. And there are many results in the paper, if you, a few others in the paper. But our conclusion is that we managed to actually assign position trajectories to all partons inside the generation. We succeeded to prepare such color connection which would give, let's say, reasonable results and distort towards the heavy ion collision, let's say. Maybe other issues is open now. That's it. Thank you.
Thank you very much, Miroslav. Other questions? We have a couple of minutes left. Okay, I don't see any. Thank you very much. And let's move to Leticia Conqueiro now.
Hello.
Hello.
Okay.
Very good. We can see your screen.
So can you see my slides now?
Yes, please
okay.
go ahead.
Okay, very good. So hello, everyone. I will be discussing a little bit about the direct and indirect observation of the dead cone with heavy flavored jet substructure. So the dead cone effect is a fundamental property of quantum field theories by which the radiation of particles from a massive particle with mass m and energy E is suppressed within a cone of angular size m over E around the emitter. So the first derivation of the dead cone in QCD was done by Donchitzer et al. 30 years ago. And parametrically, it can be described with this equation that you see in the slide. So this equation represents the distributions of the angular distributions or distribution of gluons of heavy quark Q divided by the distribution of gluons emitted by a light quark. And you can see that parametrically, this ratio is suppressed, and the suppression is governed by θ0, which is precisely the ratio of the mass of the heavy quark divided by its energy. And on the right-hand side, you can see a simple drawing of this parametric dependence for different masses, and you see how the strong suppression happens at small angles. So the fact that radiation is suppressed around at small angles has some very direct implications. The first one is that if small angles are suppressed, then this means that the hard gluons with the hard collinear gluons are suppressed. And then since QCD is divergent in that regime, that's precisely where radiation is more intense, this would lead to a reduction of a strong reduction of emissions, and then a fragmentation function that will be picked at larger values offset. And then also logically, one expects lower intrajet multiplicities. So the dead cone so far has been elusive. I mean, the direct measurement of the dead cone has been elusive. And this is because there are several complications. The main two are listed here. One is that the decays of the heavy flavor particles happen at the similar angular scales, so at small angles, and then they darken the dead cone. And also the accurate determination of the dynamically evolving direction of the heavy flavor particle relative to which radiation is suppressed is not trivial. So historically, people have used the jet axis, have used the thrust in the event, etc. So the advent of the iteratively recursive techniques opens up new opportunities. So really found with anti-KT, for instance, which is the preferred algo at colliders. And one takes the constituents of the jet and reclusters them with a given metric, for instance, the Cambridge-Aachen, which orders the constituents in angles. And then what one does is unwinds the clustering history. And then at each step, one takes the subleading prong and one registers its kinematic coordinates, KT and angle of the subleading prong, and projects it onto the Lund plane, which is drawn on the left-hand side of the slide. So the Lund plane is a representation of the intrajet emissions. Okay, so the coordinates of the subleading prong represent the coordinates of the emitted gluons through the jet shower. So the new ingredient here is that instead of following the hardest branch in the iterative process, we follow the chunk that contains the fully reconstructed heavy flavor hadron at each step. So an example of Lund plane now expressed in angle and energy of the radiator the energy of the radiator is the sum of the energy of the subleading and leading prong at each the clustering step. And this Lund plane, well, this is a relative difference of Lund planes. It's the relative difference between the Lund plane of a big quark and that of a light quark. And you can see a region which is in deep blue where there's actually no emission. So radiation is totally suppressed. And you see that it also coincides parametrically with the red line, which is the parametric line for the dead cone. So the message to take home here is that if one wants to see suppression of radiation, one should rather look at small radiator energies because that's where the effect happens at angles that are measurable experimentally. So 2 radians, so log of 1 over theta equal to 2 is about 0.1 radian. So the philosophy of all this is to use the iterative clustering to penetrate the jet tree deep enough to then reach the small angle splittings that then are sensitive to the mass effects. So experimentally, what we did in the LIS is we consider the decay channel of the D0 to kpi, which has a modest branching rate of 4%. And what we do is we perform the standard sideband subtraction. So essentially, we look at the peak region in the invariant mass distribution, and we build a Lund plane with those jets containing the D0 jet candidates. But then, of course, we want to subtract the map of splittings corresponding to combinatorial D candidates or background D candidates. So then we look into the green region in the invariant mass plot, and then also draw the splitting map. And then we perform a subtraction, so as it's written in the lower left corner. So I mean, just as a detail, you might be wondering what's the horizontal band at low KTs. So and small angles. This is splittings that come from the D star decays. So this Lund plane, that's why it's potentially very sensitive, because of course, I mean, this part is a non-perturbative part, but you can see that it's sensitive to decay or low KT splittings too. Okay, so there are also a little bit of more technical decays because we correct for the reconstruction efficiency. So the topological and the PID cuts that are used for the D candidate selection, they have finite efficiency. And also the fractions at the detector level of prompt and not prompt need to be estimated, and this we do with POHEC with reweighting with the experimental efficiencies. So essentially, we end up with a sideband subtracted Lund plane. So again, KT versus angle for the D0 jet candidates. And on the right-hand side, you see the Lund plane for inclusive jets. Inclusive means everything without a heavy flavor bias or without heavy flavor tagging. So mostly light quark and gluon jets. So our main observable will then be the ratio of the projections of these planes onto the angle axis. And then this will be done by considering cuts on KT. So KT is the scale of the splitting. So it's as simple as a horizontal cut. And then we can require the KT to be 2 times lambda QCD, for instance, or lambda QCD in order to suppress the hadronization effects and remain with purely perturbative splittings. So the fact that this is a ratio observable means that the detector effects, they cancel out in the ratio. Okay, so this is the final observable. We call it R theta, R because it's a ratio, and the precise definition is on the upper right corner. And what you can see is that indeed the splittings at low angles, so at large log of 1 over theta, are very much suppressed. And you can also see that the degree of suppression varies with the KT cut supplied. So the more stricter the KT cuts are, then the more of a suppression that we see. And here note that we are binning on radiator. Again, the radiator is the energy of the emitter in the given splitting between 5 and 15 GeV, so quite low. And then a word, of course, as I said, I mean, here we will have not only prompt Ds, but we also have non-prompt. And then this means that there are B hadrons that are decaying into these D zeros. So this means that there are extra pi's from the B hadron decay that will generate extra splittings at low angles. And in general, they will darken a bit the dead cone effect. But this is like a 10% contribution that we have estimated. So another thing that one can do is to check how this dead cone suppression increases with radiator energy. Parametrically, we expect that the larger the radiator energy, then the less of a suppression. And this is what we see here when we go from 5 to 15 GeV. And okay, so now, as I said, so this is a direct observation because we are really looking at the distribution of the splitting angles. But now let's see what happens to the intrajet multiplicities. And one way to quantify it is to look at the NSD. So the NSD is the number of subjects or the number of prongs that satisfy the soft rock grooming condition so that they are sufficiently hard. And what we see is that for these zero tag jets, in general, these zero tag jets have less prongs passing the soft rock cut than inclusive jets in blue. And when we look to Pythia, what we see is that for this difference between these zero tag and inclusive, there are also other contributions because, of course, there are color factors, right? So, so also light quarks have fewer NSD prongs than gluons. So both color factors and mass effects are contributing to this, potentially contributing to this difference that we observed experimentally. So from this point of view, the ZG is perhaps more interesting because the ZG, which is the momentum balance of the Groom splitting, this is theoretically proved to be so color average. So it doesn't depend, it doesn't change for light quarks of gluons, as you can also see on the Pythia simulation on the right. So the ZG is similar for light quarks and gluons, and then it sticks out for these zero tag jets. So here we are potentially isolating mass effects, and experimentally we have some hints that the ZG distribution is more asymmetric in the case of these zero tag jets than inclusive, and this is consistent with harder fragmentation for heavy flavor quarks. So I reach now to my conclusions, and then well, yes, this is the first direct measurement of the dead cone. We've looked at the splitting angles in detail, and we've also used the Groom jet substructure like the ZG or the NSD to probe the direct consequence of the dead cone, which is the harder fragmentation and also lower intrajet multiplicities. And very quickly, I would like to say 2 words on prospects. One prospect is run 3. So the run 3 projections that we've done tell us that we'll be able to measure the dead cone in a list in PP using fully reconstructed B hadrons, and this is a very nice opportunity. So this is the R theta for B tag jets to inclusive. So we will be able to scan the mass dependence. And then the next step would be to look at the dead cone in heavy ion collisions, because in heavy ion collisions, medium induced radiation is not expected to respect the vacuum rules, and it's expected to fill the dead cone. And perhaps this brings a very interesting opportunity to explore a region of phase space where the vacuum radiation is suppressed and then everything's dominated by medium induced signal. And this is the end. Thank you.
Thank you very much, Leticia. Are there questions? Yes, Hannes.
Hello, team. This is a fantastic result. I'm very, very excited about that. You say only in the next run you can do B analysis on B hadrons. Why is that? Is it because of statistics, or because you need to fully reconstructed B, or?
It's because, yeah, so the thing is that in order to get the subjet energy at each step, And also to avoid decay particles darkening the effect, we really need to reconstruct fully the hadron. So then for that, yes, it's mainly a matter of statistics and significance. So it's only with an increased statistics of run 3 that will be able. So now, I mean, maybe reconstructing bees via electrons could be possible, but yes, when you don't fully reconstruct the heavy flavor prong, then the effect is diluted. So
thank you.
Any other questions for our speaker? Okay, if not, let's thank her again and
thank you.
Move to our last talk before the break, which will be by Matthias Schott on QCD instant stone at the LHC.
Okay. I guess I can start?
Yes, you can go ahead.
Okay, let's just directly go to the next slide. Okay, so you might have heard of instantons before in your very basic quantum courses, because actually it's a very well-known process. The basic idea, what you see here on the lower left, is such a double well potential. And one way to solve it is by just inverting this potential, then calculating the classical solution and transform this back to a quantum mechanical solution. And this tunneling process between this well is actually an instanton. Now, Toft already realized several decades ago that the same concept of instanton solutions can also be extended to any Yang-Mills theories. So any non-abelian nature of the Yang-Mills theories leads exactly to this effect. And what you see here on the lower right is such a kind of illustration. So there we have a vacuum with several minima. And what you typically do is use perturbation theory. You just choose one minima and develop around this. However, what you typically ignore are processes, tunneling processes, which are called instantons, or processes which are going, across this potential, which usually are called Sullivan processes. Okay, so that's what instantons are. Let's go to the next slide and see where this comes into the game when we look at QCD and electroweak theory. So for the electroweak theory, these instanton processes or Sullivan processes are associated to the baryon and lepton asymmetries, or baryon-lepton number violations. And actually, that's rather crucial for the evolution of the universe. So the same effect, as I just showed you, has to happen in the QCD. And there, actually, it's thought that these QCD instantons are also solving several problems like the axial U1 problem or chiral symmetry breaking. Now, very important now is obviously how big this barrier is between one and the second vacuum, which you saw on the previous slide. So you can calculate this for the electroweak sector, and there you see that this barrier height is roughly 10 TeV, and actually means that if you would like to look for these effects in particle collisions, the FCC wouldn't be enough. You need something like 200, 300 TeV collider to be able to see this. However, the situation is completely different in QCD, because there the barrier high is given by this expression which you see here. So it's 3 pi over 4 alpha s and rho effective. And this actually scales with Q. So in some sense, if you go to very small, couplings or effective sizes, then you can change this size of the potential. That actually means that you can be in principle able to see these effects, these instanton effects in QCD. So in the next slide, actually, looking for these effects is not completely new. Actually, this was already done at the Hera Collider. Actually, most of the literature so far has been looking into QCD instanton effects in electron-proton collisions, which is schematically shown here on the right side. In principle, here the process is characterized by 2 scales. First, obviously, by the available energy of the collision, but then secondly, here by this outgoing quark, which you see here as Q double prime. And the reason why this was introduced is simply a theoretical reason, simply because to get an infrared safe prediction on these instanton contributions. Now, actually, then this was looked for, and then they have been setting upper limits on the actual cross-section of these processes. Now, the complete picture is a little bit different for the QCDs at Hadron collisions, because there actually it's quite difficult to have such a second scale parameter, and both of the incoming partons are therefore on the mass scale. And as you will see in a second, this actually results in QCD instanton-induced scattering processes, which produce something like soft bombs, which you can imagine as a decay of mini black holes. We will see this in a second. So let's go to page number 5. So actually, the following presentation now is based on this publication, which I did together with Valia Kose and Frank Kraus. And since I'm the experimentalist in this group, unfortunately, I have to talk now in 8 slides about stuff which I only vaguely understand. So let's see how well this goes. So in the approach which was taken in this paper here, only small instanton processes contribute to the scattering process of QCD. And then once you think about this multi-final states, and obviously one thing comes always up as a critics, that one cannot make a Fisher Hadron Collider. Essentially says that high multiplicity final states should be largely depressed. While at the electroweak theory, this is obviously already true simply by the fact that the barrier height is so high. However, for the QCD part, they actually will see in a second in some slides that the Hadron size also falls with increasing center of mass energy, and we get a quite high suppression of scattering rates when we go to smaller energies, as you will see in a second. So this critics, I think, doesn't play a role for us in this case here. So let's go to the next slide and go a little bit more into the calculation itself. So what we want to calculate is actually this process which is shown here. So 2 gluons go to this instanton, and this instanton process leads to the generation of several gluons, as well as all available quarks and antiquark pairs, which are in the kinematic range. We will discuss this a little bit later when we come to the implementation in a generator. Also quite important for this process is that there are no fermions of opposite chirality. So no left-handed quarks nor right-handed antiquarks actually are produced by this process, which actually is a core prediction of the QCD. So then we also can look at quark-initiated instanton processes, looking by this, looking at the formulas below here. Essentially, we get this by just inverting the 2 of the outgoing fermion legs into incoming antifermions in the initial state, and then do the calculation. So let's go to slide number 7. So essentially, the basic idea here is that we can calculate this via the optical theorem. So compute the imaginary part of the 2 to 2-fold scattering amplitude, which is actually shown here. So now let's look a little bit more detailed into this expression, what we actually have here. So the integrals here go over all collective coordinates of all of the instanton, anti-instanton configurations which we have. So rho and anti-rho are the instanton and anti-instanton sizes. Mu is a separation between the, or a small mistake, between the 2 instanton positions in the Euclidean space. And omega is now a 3x3 matrix, which specifies the relative orientation in the SO3 color space. Now then you see there are more factors or terms in this integral. So you see this d and this exponential here. So let's see what that is. So let's go to the next slide. So there you see the d. So this is essentially the instanton density given by the one loop expression by Toft, which we use. So this is actually a rather old paper already. And this is just this expression here. You can plug this in, and most of the constants are known. And then there is this exponential factor e to the minus s double I, which is a semi-classical suppression factor for the process of the action of the instant anti-instant configuration as shown here. So s I can be separated with these terms, whereas I simple is the action of the single or anti-instanton action, and U int is the integral between the potential of the instanton and anti-instanton, which can be now attractive or repulsive. And actually here the general expression was already calculated in 1991. So this is also known. Let's go to the next slide. So actually now this instanton anti-instanton action can be rewritten by the dimensionless variable, which we call now psi, which is r over rho. So rho again was the instanton size, and leading to the expression which we have here. And this can be computed, and this is actually shown here on the right-hand slide. A bit more interesting is the lower plot here, where actually you see the leading order contributions, which are the dashed lines, and the next to leading order contributions, which are shown here as dotted lines for this potential independence of psi. Okay, so once we have this, we can again go one step further to slide number 10. And thank you. And then taking also into account the Fermi contributions, we get to this expression. So the previous expression just plugged everything in what we had so far. So the problem now is, and this is why these full predictions of this QCD instanton processes are rather uncertain, is that this suffers from severe infrared problems when we go to very large instanton sizes. Now, the basic idea to break this or to solve this is that we can break this classical scale invariance by inclusion of quantum corrections that describe the interactions of the initial state gluons. And this idea actually goes back already to a paper by Müller in 1991. And this is actually what we use here. So we use and put this in. That actually, this is in some sense our solution to the idea which was at Hera to use this scale variable to suppress this effect. Okay, so we put this in, and then we go to page number, slide number 11. I have to hurry up a little bit. And we get now to this final cross-section on parton level. We do the calculation. Well, actually, this was done by Valia. And if you want to hear the details, invite him for a seminar talk or read the paper. Important now for us is here the table here on the lower right, where actually you see now the final cross-sections of these instanton processes. Okay, so this is only on parton level. So if you go to page number 12, you briefly see how we included this into the Sherpa generator. So essentially, we just integrate now the parton density functions over these cross-sections which Valia provided us on parton level. And then actually you get shown here in this table below the next the actually proton-proton cross-sections using NNPDF 3.1. And now that's obviously gets interesting because once you get to when you have small energies, it's a very sizable cross-section of 6 millibarn, and you can get then obviously this decays exponentially. So we get something like 3 femtobarn for 500 GeV center of mass energy. Let's go 2 more slides I have. So let's go to page number 13. What are we, if you want to see this, find this perfectly fine, page 14, thanks. So if we want to see these observables, or if you want to see an instanton process at the LHC, what you would looking for? Well, obviously this depends a little bit on the available center of mass energy. If you look at low instanton masses, so small s, then you would expect many tracks. And these tracks actually should be spherically symmetric. And there should be many of them. And they should come from all the quarks. So U anti-U, D anti-D, S anti-S, C anti-C. If you go a little bit wider, then you get also tracks from B anti-B. If you go to higher energies, then you would expect jets, lots of jets, again, spherically symmetric. The problem obviously is, and there are some of the distributions here, the problem is if you go for low energies where you have high cross-sections, then clearly this is very similar to underlying event. Now you have to come up with a strategy how to distinguish normal underlying event from these instanton processes. And one idea would be, for example, that you fix your models for the underlying event in the forward region of your detector, and then search for the QCD instantons in the central part, simply because they're expected to be more pronounced. Okay, let's go to the last slide already. Okay, I discussed this already. Let's go to page number 16, just to the summary page. Okay, so this would be, this whole talk was a small teaser that I think you should, or we should start looking for QCD instantons, simply because they're the last prediction of the standard model, which has not been experimentally observed. I mean, by last prediction, the last core prediction that this should exist. And what we showed here was the first calculation on the instanton processes at the LHC and the implementation in Sherpa 3.0. I think it would be good to have a next calculation where we use a Hera style setup. I mean, by forcing one particle to be off shell and do the calculation again. And then you see also on the last slides some promising observables for dedicated search for QCD instant processes at the LHC. And that's already the end of my talk.
Thank you very much, Matthias. Very interesting talk. So there is a question by, I don't know the name, but go ahead, please.
Sorry, I hope you are talking about me.
Yes.
Unknown name.
Unknown name, exactly.
It's known to me. No, actually, I have a question because, hello, Matthias.
Hi, how are you doing?
I mean, you are talking about instanton production at the LHC, but when I am completely far from this topic, but you were showing the cross section, and the cross section was much bigger for lower energy. So
yes.
does it mean it is better to look for instantons at lower energy at RIC or some other accelerator or SPS?
So a very good idea, a very good question. So the problem, so the cross section actually is okay. Good question. The problem with these calculations is that there are assumptions on the on how the instanton behaves at small energies, right? And unfortunately, our predictions, I would trust them maybe to 1 or 2 orders of magnitude of size. So the problem what we have is when you go to very low energies below 20 GeV, which I showed, then rather soon your instanton cross-section gets larger than the overall proton-proton cross-section. And obviously this is nonsense. So apparently it's just a sign that our calculation breaks down at some point at small energies. And that's the full problem. Yeah. So this calculation gets reliable more and more that you get to higher energies. When you get to low energies, then essentially it loses any predictive value.
Thank you very much. Thank you.
Are there any other questions for Matthias? Okay, if not, thank you again. And I would like to thank all the speakers of this morning. We'll have now a short break and we'll reconvene at 9:40 for the next presentation. Thank you, everyone.
Hello, the speakers for the next part of the session. Can we check your connection in the slide sharing? I think the first speaker is Borulin.
Yes, this is Boru.
Hello.
Hello, let me try to share my screen. Right.
Yeah.
You can see the slides already?
Yeah, just
okay.
change the slides to see if everything
right.
works.
Let me see. Right, I think.
Yeah.
Right. Okay, cool.
Very well, thank you.
Thank you.
Then we'll have Anton Čurek.
Yes, I am here.
Hello.
Share screen. Hello, hello. Share screen. And how I screen. Okay.
Very well.
Is that okay?
Yep. Okay. Thank you. Yeah, it works fine. Then next speaker is Rafał Staszewski. Do we have Rafał connected? Not yet. So maybe Rafał Sikora, if can you hear me? Or Rafał Staszewski. Rafał, if you hear me, can you just check that your slide sharing works?
Hello, Sharka. So this is me. I understand that I should also be sharing video. Hello. Does it work?
Hi.
Okay, I think it works. Let me try to find the slides. Okay, and let me try sharing.
Yep. Yep.
Okay.
Works fine. Thanks.
Thank you.
And the next speaker then is Rafał Sikora. Rafał. Not sure he's connected. Maybe not yet. Anna, I think we already tested your sharing, right? Would you like to try again, or it's okay?
Yes, we checked before the first session.
Yeah, I think it's okay. So Arthur Bolt.
Hi, can you hear me?
Yeah, very well.
Good, and then I'll also try to share my slides. So these are here, and I can change slides.
Works very well, thank you.
Thank you.
And then our last speaker will be Otto Nachtmann. Is he connected? Okay, I don't hear everybody. So let's say for the moment we are set up, and we hope that everybody will be here when his time comes. So we will start in about 5 minutes. I see we have now Otto Nachtmann connected. Would you like to check? Will you share your slides, or do you prefer that we share them for you?
Yes, I have the slides on the computer here, so it should be all right. Should we try out?
Yeah, that would be maybe better.
Yes.
Just
so
as a practice.
Then, yes, just a minute. But
if the host stops sharing, maybe for a minute. Yeah, thank you.
Okay, so try again. And so now I click here, double click, Thailand. Ah, here it is.
Yeah, perfect. Okay,
That's
very
right.
well.
Thank
Excellent.
you. So was my yes.
Thank you very much. Okay,
so it should work. Thank you.
Yeah,
all right.
Thank you.
So now.
Okay, so I think we
start.
Yeah, you stopped sharing. I think it's okay. So welcome to the second part of our session. We'll hear mostly. My name is Sharka Todorova. I will chair you through this part, which is devoted mostly to exclusive and diffractive processes. And our first speaker is Po Julin from the Compass, who will be talking about deeply virtual quantum scattering and exclusive meson production.
All right, so this is Peru. Thank you. I will try to share my slide. Hopefully you can see it already.
Yeah.
Okay.
Well,
it's my pleasure to present you the DVCS and exclusive meson production measurement at the Compass experiment on behalf of the Compass collaboration. Firstly, the Compass experiment will be briefly introduced, followed by the discussion on the deeply virtual quantum scattering, DVCS, and hard exclusive meson production, HEMP, and finally a summary and outlook will be given. Oh, sorry. So Compass is a fixed target experiment located at CERN, utilizing the M2 beam line at SPS. So Compass has the luxury of receiving a variety of hadron and lepton beams. For the highly exclusive measurements, the polarized muon beams of 160 ICHEP were used. So in the picture given in the middle, the incoming muon beam, which has opposite polarization with a different charge, would impinge on the LH target. And then the thus generated particle would penetrate through the two-stage large angle spectrometer of Compass, which consists of two dipole magnets, SM1 and SM2, 3 stages of electromagnetic calorimeters, ECAL 0, 1, and 2, and different stages of tracking and triggering stations. So a key ingredient for the exclusive measurement is the recoiling proton detector, which is called camera. That is consists of 2 rings of scintillators with LH2 target in the center and try to detect the proton in terms of the TAOF technique. So after a successful pilot run of 4 weeks taken in 2012, there were dedicated runs taken in 2016 and 17, and about 10 times more statistics were accumulated. So here I present you the kinematic coverage of different experiments in terms of Q-square versus X-Purican. So in the low with the low X-Purican covered by the H1 and Zeus data, and with the relative higher X-Purican covered by the Hermes and JLab data, you can see that the Compass kinematic coverage, which is given in the shaded green, okay, a little bit overlap with the Hermes, but it has its unique place in the C-quark domain before the EIC era. So DVCS, the plot on the left shows you the so-called handbag diagram, which represent the leading order and leading twist DVCS process. So in the diagram, you can see that the virtual photon is emitted by the incoming lepton, which is then absorbed by a parton coming from the proton carrying a longitudinal momentum fraction of x plus psi. Then this parton emits a high energy photon in the forward direction, then recombines with the rest, keeping the proton intact back while leaving a small forward momentum transfer T to the proton. So DVCS has been regarded as the key golden channel for the probing of GPDs, which encapsulate the transverse position information with the longitudinal momentum distribution. And it interferes with the very well-known beta-Heitler process, where the real photon is actually emitted by the leptons, so that it provides a handle to crank out more information from the process. So experimentally, the measurable that we have is the energy of the lepton, the virtuality of the virtual photon Q square, and X puricant that can be related to the psi, so-called skewness, and the forward momentum transfer T, and the phi, which is the angle between the lepton plane and the virtual photon plane. The photon plan. So with these measurables, we try to access information of the GPDs that depends on these variables X, psi, T, and Q square. And at the small X puricant coverage of compass, we focus on the measurement of GPD edge. But with that being said, what actually is measured in the experiment is the so-called Compton form factor CFF edge, just due to the fact that X is not a direct measurable in the experiment. So CFF edge is a GPD edge integrated over X, and the real part and imaginary part of then is intercorrelated with the presence of the D term. So being interesting and important in its own right, the investigation or the study of CFF edge is interesting because it can be correlated to some interesting properties of the nucleon. So the imaginary part of the CFF edge can bring information on the transverse size or extension of the parton in the nucleon. And it would be interesting as well to see how it evolves as a function of X, while the D term can provide insight into the pressure distribution in the nucleon. So by doing this so-called beam charge spin sum, which sums up the cross-section that we get from the mu plus and mu minus, we get contributions from the beta-Heitler, DVCS, and also the interference between them. To extract out the DVCS contribution from the rest of the other terms, we try to examine the X puricant dependence of each of them. So the three plots on the top shows you the phi distribution of the event with increasing X puricant from left to right. So in the left plot, you can see the data, compass data represented as the solid circles is well described by the beta-Heitler Monte Carlo, which is given in the black histogram, which shows a beta-Heitler dominance is in this small X puricant regime. While going going for a higher X puricant, we can see the data now just cannot be fully described by the beta-Heitler together with the pi0 background. So then we can, at this high X puricant regime, we can then take out the beta-Heitler contribution, remove them, and with the symmetric in 5 of the compass acceptance, those 5 dependence terms can be integrated out. So we are left with the C0 DVCS term, which is can be linked to the imaginary part of CFF edge. Okay, then that brings bring us the information of the transverse extension of the parton. So the cross-section as a function of T, which is given in the plot on the left, is fitted with the exponential dependence, where the so-called exponential slope parameter B extracted is 4.3, and that can be translated into the transverse size, or represented as R perp here, of the parton, and that is about 0.58 femtometer. So the plot on the right shows you the compass result given as the solid red circle together with the other data coming from HERA. And in the plot, you also see the model predictions coming from KM15 and also GK parameterized with the Q square from at the minimum and maximum of the data covered in this plot. So with the 2016 and 17 data, with 10 times more statistics, hopefully Compass can provide 3 more beams in the data. I mean, in the Compass coverage here, so that we can have a better view of, or say, insight into the transverse size evolution as a function of X puricant. So a quick glance on the progress on the 2016 and 17 data. So we have comparable result of these plots showing you the data and beta Hadron Monte Carlo comparison using only 13% of the 2016 and 17 data. So we're progressing on this, and we give a big thanks to the Blue Waters computing facility, which helped a lot in generating these results. So, the universality of the GPTs also grants us the ability to probe them with the meson production, which is like illustrated in the plot on the left. So in addition to the 4 chiral even GPTs that can also be probed by the DVCS interaction, the meson production also grants us access to these 4 chiral odd, or sometimes called transversity transverse GPTs, with the subscript of T in each of them. And often we see this ET bar term that is represented as a combination of HT tilde and ET. So since different mesons would carry different quark and content, also quantum number, it can act naturally as the quantum flavor filter. So with the ability to probe the chiral GPTs, the meson production is complicated by the involvement of the non-perturbative term from the meson wave function. So in addition to the study of nuclear structure, the meson production also provides us insight into the reaction mechanism. So firstly, about the pi0 production using the 2012 data in COMPASS, the differential cross-section can be, for the pi0 production can be decomposed into these terms, representing sigma t, sigma l, which represent a different polarization of the virtual photon, and the sigma tt, sigma lt is the interference terms. So sigma l term has been as the leading twistor was expected to be the dominant term, but it was found out that it's only is just a few % of the sigma t term. And for the interference term, one term that is of special interest is the sigma tt term, since it simply depends on the ET bar of the GPT. So the extraction of the different terms of cross-section can be checked through its different dependency on the phi, and the extracted result is shown in the plot on the left. So for the COMPASS result, we see a large contribution, or say a significance of the sigma tt, which indicates a good impact coming from the ET bar. And we measure the sigma LT term is smaller, but it's positive significantly. So the plot on the right shows you the dependence on T of the cross-section together with the predictions given by GK. So the COMPASS result is shown as the solid circle, while the GK prediction is given in 2 curves, one with the COMPASS data, which is the lower curve, and the one without the COMPASS data, which is the upper curve. So that you can see with the inclusion of the COMPASS result, the model prediction of GK actually gets scaled down by a factor of 2, which shows the importance of the COMPASS data in putting the constraint of the GPT modeling in the kinematic coverage of COMPASS. Okay, then for the study of exclusive omega production, by studying the angular distribution of the omega production, we can extract out 23 spin density matrix elements with SDMEs, and they can be categorized into 5 different categories depending on the helicity transition from the gamma star to omega. So under the scheme of the S-channel helicity conservation, it implies that some terms of then in the sector A and B, that they should sum up to 0, which is checked within error. But also SCHC, this helicity conservation also says that all elements in this sector C to DE should all be 0, and which is clearly violated in this section C. And one term that is R500 that is definitely violating the SCHC. In the study of Gloskokov and Kroll, they correlated this fact to the presence of the ET bar and HT. And this complements the previous study done by COMPASS as well in the rho and omega production with the transverse polarized target. So we were trying to submit this result to arXiv very soon, hopefully in the next few weeks. So a quick summary, I've talked about the study of GPDs, which involves the study of the imaginary part of the CFF edge that can provide us the information on the transverse extension of partons. And with the inclusion of 2016 and 17 data, we can do this beam charge spin difference. Then we will try to extract out the real part of the CFF edge, and together we can get the D-term for the pressure distribution. So in the as to the HEMP, in addition to the pi and omega production that was discussed, we have studies going on with rho, phi, or J side production as well. So it's a pity that due to the time limit, I cannot go through all the details of them. But hopefully the point is made that with the data provided by Compass, it's going to give us a fruitful insight into our understandings of the transverse GPDs, and also hopefully will help on the flavor decomposition. So we have ongoing analysis on the 2016 and 17 data at this moment, and we're pushing forward to the release of new results. That would be all. Thank you for your attention.
Thank you for this nice talk and important measurements. We have time for just one quick question. Anton? Anton Šurek?
Hello. Really very good talk and interesting results. I'm interested in this very quick dependence on the T distribution, which is going down, whereas exactly on this figure, whereas even if Goloskokov-Kroll model is adjusted, it has no this minimum close to 0.6. So the question is that maybe this is multiple scattering effects, which creates, actually we don't know what is this minimum, but I think such effects, some signs of such effects are observed in other reactions. So, okay, so I don't know if the formalism is sufficient to describe your data. This is my comment.
Right. Exactly. We noticed this discrepancy at the high T prime, behavior as well. I believe that Peter Kroll is trying to tune something on that, but since we're not sure, and definitely there is something that need to be compensated into the match of the data with the model in this high T behavior, for sure.
Okay, I think we have to move on. Thank you very much.
Thank you.
And Anton, please stay unmuted. It's your turn now. So next speaker is Anton Šurek, talking about inclusive production of F2 tensor mesons at the LHC.
Okay. Sharing. I'm going here. Sorry, I have problem.
Yeah, we see your slide.
Okay.
Go ahead.
Okay, thank you. So I start more or less on time. So I will be talking about inclusive production of tensor meson at the LHC, and the mechanism I'm going to consider is gluon-gluon fusion. And this will be done in the KT factorization approach. This is work done together with Piotr Lebiedowicz. It was put on archive last week. Actually, we want to put even corrections to this paper already. So I will present short introduction. Here I will mention about quarkonium production, pseudoscalar and scalar quarkonium production, where the gluon-gluon mechanism seems to be the dominant mechanism. Also, last months we studied production F0 980 inclusive production, where gluon-gluon mechanism is important, but certainly not the dominant mechanism of the F0 production. And here I will discuss production of F2. So we will start from gamma-gamma going to F2, and then we go to gluon-gluon to F2. This will be done KT factorization. I will use different unintegrated gluon distribution, and I will mention about some pi final state rescattering effects, which must be present also. So introduction. The string model is usually considered as a mechanism of production of hadrons. However, as far as F2 is considered, there is very little produced via string models in F2, and PYTHIA cannot reproduce the data I will show in the moment. So there's a question how F2 is produced. So gluon-gluon fusion was considered for eta C and chi C in our paper, which I will show in a moment. The question of some isovector light meson production is really, I would say, terra incognita, and we just started to look at this. And gluon-gluon fusion is one of potential mechanism which can be important, and you will see where we are in the moment. So these are our recent papers. So first one is on eta C production. Second, Isabella Babiasz was talking about this. Second one is about chi C0 production, not discussed at this conference. This is about F0. And now I'm talking about this new archive. So the mechanism I'm talking about is gluon-gluon fusion going to F2 tensor meson. And this is inclusive measurement, so I don't care about what else is produced. So first of all, I should start from the vertex. And before I go to gluons, I go to photons. And actually, photon coupling to F2 was studied by our friends, Otto Nachtmann and collaborators. And actually, they have written the vertex, corresponding vertex by two tensorial structure, one corresponding to helicity 0, second corresponding to helicity 2, and this tensorial structure were given in their analysis. Of course, there is a question that we don't know coupling constants. It is very difficult. It's non-perturbative. These are non-perturbative effects. So to extract coupling constants, we need some data. And actually, our friends obtain this coupling constants by adjusting to radiative decay width of F2 to gamma gamma. There is some freedom in setting how much is 0 helicity and how much is 2 helicity. The general conclusion is helicity 2 dominates and helicity 0 is 9%, but perhaps even less because there are some other effects which I am not going to talk about this. So the decay width can be expressed in terms of these couplings of our friends in this way. And these couplings are shown here. I omit here signs only absolute. I am showing absolute values. There is another approach, Pascaluzza, Pauk, van der Hagen, and this also started even earlier by Poppe, which consider general structure of photon-photon to tensor mesons. And they have shown that in general, there are more couplings. When we go off-shell, there are more couplings, and there can be 5 different couplings. And here I am showing their result of the coupling for virtual particles. And you see this 5 in colors. You see form factors related to those couplings. Of course, those form factors are not known. In Otto Nachtmann and collaborators approach, there are only this T2 and T0T form factors and no others. However, anyway, we don't know much about these blue form factors, which I will mention. Here there are some technical things which I think I can skip to accelerate a little bit. We have checked that these two approaches, EMN and PPV, are equivalent on mass shell if we do the following correspondence between them. If we do this, they are fully equivalent on mass shell. However, as you will see, off mass shell, they are different if we use the same form factors. Of course, this is a complicated story. What are form factors for photon-photon going to F2, but also for gluon-gluon going to F2. And in our paper, such form factors, we tried different forms of the form factors, some motivated by PQCD, some motivated by some other approaches, some vector dominance. Actually, I should mention, maybe this is not nicely presented here, but before us, there was a calculation on F2, inclusive F2 production by Yeon and collaborators some maybe 15 years ago. I don't have date here. So they also consider such approach with a little bit older gluon distributions and special coupling. So I will be talking about KT factorization approach. So the cross-section, inclusive cross-section, which depends on rapidity and transverse momentum, depends on gluon unintegrated distribution, gluons, and off-shell matrix element. And we calculated off-shell matrix element. And gluon distribution we take from the literature. We take gluons which describe many other data I will mention, but just to mention it shortly now, Kimber, Martin, Riskin, which describe nicely, for instance, charm production, or Jung, Hautmann distributions, which are fixed to deep inelastic data. So this is CCFM approach. There is no time to talk about gluon distribution. This is technical slide how to calculate matrix elements for KT factorization from usual vertices. This is written here in the KT factorization, but I am not going to discuss. And here I am going to the result of Yeon et al. From 15 years ago. He has written general structure, but he assumed that photons couple to F2 via energy momentum tensor. And this is his result. This is a little bit long formula, and I'm not going to discuss this. But there's a question how this formula compares to the vertices which I mentioned, this Heidelberg group and Mainz group. In order to go from photons to gluons, I had to replace electromagnetic couplings by strong coupling constants, and also include color factors, and also include fact that when photons couple, you have to include charges of quarks, and you have to take average squared charge of quarks, which is this amount when assuming such flavor structure. We are taking running coupling constants, and in the infrared we use so-called Shirkov-Solotsev prescription how to extrapolate down to small renormalization scales. I want to mention that in this old calculation, the strong coupling constants were completely ignored. I mean, they are running and everything was put to one normalization factor. We will consider also another mechanism, because in high energy collision, proton-proton, there are many pions produced, and F2 could be produced as an effect of final state interaction of pions. These pions can create F2 in the final state. And here we also made some little model in order to see what can happen. We know that we will be talking about 7 TV energy and Alice data. We take data for pions, and we parameterize this distribution, which are written here in this formula 24, by some phenomenological form, Levy parameterization. This has no importance for us. And now we are considering model which is quite similar to color evaporation model used for J-psi. So to calculate number of F2s from those pions, we do such a convolution. And here there is some magic parameter, probability to form F2 by pi-pi fusion, and this is probability of formation and survival, and includes everything. So this is why I'm saying it's magic number. And we are doing this convolution using this data for pions and using Tsalis parametrization of those data. Recently, there was some work by Utheim and Sjostran, which considered this more sophisticated way. However, I didn't see comparison to experimental data. Experimental data show dn over dpt, so we have to transform cross-section by using inelastic cross-section, and we use a recent measurement of Totem and Atlas average value of this in order to get these numbers. And now I'm coming to experimental data, and this is a first result. This is experimental data which was presented in Lee thesis some years ago, so I call it preliminary ALICE data, and our calculation. So you see on the left panel we are using Heidelberg vertex with different form factors, and on the other plot Mainz form factor with different form factors. So you see everything depends on form factors, and some form factors are excluded. Some form factors are almost fitted the data at larger PT. In principle, they could be adjusted to the data. We didn't do such fit because this is first study, so we want to understand the situation. So these form factors are crucial, and depending how you parameterize them, you can get different results. Of course, you cannot exceed the data, so this is a condition. In this calculation, we are using Jung-Hautmann unintegrated gluon distribution, which worked also very nicely for eta C production. Here I am showing two contributions, helicity 2 and helicity 0 for Heidelberg vertex and for Mainz vertex. And you see they are different off-shell. This is PT of the meson, which depends on virtuality of gluons. So result is different from these different vertices when and the composition into helicities is also different. Here I am showing, maybe I will skip the left panel where I compare Mainz and Heidelberg vertices, and I go to the right panel when I'm showing Gaussian distribution, which are often used for unintegrated gluon distributions. So here you show that I'm showing results for different sigma zeros, smearing parameter. So there's no sigma zero which can describe as data with Gaussian distribution. So this is such a simple check. Now I'm going to two-dimensional distribution, transverse momentum of one photon versus transverse momentum of the second photon for Jung-Hautmann unintegrated gluon distribution, and on the left-hand side with Heidelberg vertex and Mainz vertex on the right-hand side. These two look very different in this broad range. So it means these vertices are not completely equivalent. However, let's concentrate on this corner close to 0, 0. And we checked that in this regime, these two comes to unity when transverse momenta go to 0 and both transverse momenta go to 0, 0.
Anthony, you are running out of time. So
okay, thank you. So shortly, I am almost finishing. We also try to analyze these other terms which are in Mainz vertices with helicity 1 and some others. Of course, we don't know. We have no clue how to find them. But if we assume similar form factors for them, they could be important at large virtualities. So it means at large PT of the mesons. We have also tried, this is last transparency, we have also tried to look at what is contribution of exclusive processes, which we studied with Otto Nachtmann, and its contribution, this dotted line here, red, is very small, so cannot explain. The blue line is pi-pi vertex, and this black lines is gluon-gluon fusion. So you see these two contributions compete, gluon-gluon fusion and pi-pi rescattering most probably. So, so I am skipping to conclusions, but I will not repeat my conclusions for this short talk. Thank you. Sorry for being too slow.
Yeah, unfortunately, we don't have much time. Thank you very much for these calculations, for the comparison with the data. Unless there is a very, very urgent question right now, which I do not see, we thank you again. We are looking forward for the rest of the story. I think there is still work to be done. Thank you very much.
Thank you.
And we will move to our next speaker is Rafał Staszewski, who will be talking about the measurement of soft QCD and diffractive processes in ATLAS.
Hello, can you see my slides?
Yeah.
Very good. So thank you very much for the introduction. In my presentation today, I will cover two recent measurements from ATLAS in the topics of diffractive physics and minimum bias interactions. I will first discuss with the measurement of single diffraction. So here on page 3, I would like to briefly remind the kinematics of the process that we are interested in. So this is single diffractive dissociation and colorless exchange between the two protons, with one proton dissociating into a system with some higher mass than the mass of the proton. The three relevant variables that I will discuss is T, which is squared for momentum, transferred from the proton. It is related to the scattering angle and transverse momentum of this outgoing forward proton. Another variable is psi. It is related to the energy that was lost by this proton and transferred into this higher mass state X, and you can see the definition here. And the final variable is the rapidity or pseudo-rapidity gap between the first particle of the X system and the edge of our detector that we use for measuring this pseudo-rapidity gap. First, let me remind you some history also. We were interested in ATLAS in this process already for quite some time. Here you can see an example from an analysis from 2012 already, where we looked for large rapidity gaps using our calorimeter detectors. And by requiring large gap sizes, we were able to reduce the non-diffractive contribution. However, it was not possible to distinguish single diffractive from double diffractive dissociation processes, because when you just use calorimeter, you can still have double diffractive dissociation where one of the dissociation mass is small, so that you don't really see the second dissociation, and you cannot distinguish this from a process where only one proton is dissociating. In order to do that, one has to use a direct detection of this forward proton, which we call forward proton tagging. And for that, we use a dedicated system of detectors, which we call alpha. These are detectors using the Raman pot technology, where the detectors are operating inside the actual beam pipes of the LHC accelerator at the distance of only a few millimeters from the beam. This is possible using a special dedicated optics of the LHC, and requires special setup. So it's not a very straightforward data taking, but it is possible. The data that I will be discussing uses exactly was based on exactly such run. This is coming from 8 TeV running. Beta star, which defines this optics, was 90 meters, and also this made pileup very small, but also this means that the luminosity was quite small. We measured this intact proton using alpha. The dissociated proton was measured using ATLAS tracking detector. For the trigger, we used alpha in coincidence with dedicated triggering detectors, which we called MBTS, from minimum bias trigger scintillators. These are scintillating detectors that are installed in the forward rapidity region in ATLAS and can be used for triggering. The acceptance and the fiducial region for the measurement is defined here. So it is coming from the limitations of our detector. This is the limitations on the measurements of charged particles. Here is the MBTS range, and the kinematic range of the regarding the proton is coming from also from alpha detector. On slide number 6, I would like to briefly discuss the event selection and the detector properties. So we required that there is exactly one reconstructed proton in 2 stations that are on the same in the same armlet, and in addition, we required an elliptical cut in the plane where on one axis is the position of the trajectory, and on the other axis is the angle of this trajectory. So you can see here that for the simulation signal process, we expect this to be this kind of elliptical shape. But when you look at what we see in data, this shape is very different, with many events far away. Please take a look. The range of the axis here is different on these two plots. So we remove much of background coming, for example, from halo, beam halo events. We remove by that way. And also we have some imperfections of our detector apparatus, which leads to smearing of the observables that we measure. Here you see the matrix is describing this smearing, and this was all taken into account and corrected by unfolding procedures so that the measurement can be interpreted without the understanding of the detector. The main background that we have, the first one is coming from coincidence between a proton in alpha and unrelated activity in the central atlas, which is mainly coming from non-diffractive minimum bias interactions. This is the largest background, and we estimate it using data-driven techniques and control it in a dedicated control region. And you can see here that the description of this background is quite nice. The dominant physics background is coming from central diffractive events. So we estimate it using Monte Carlo simulations and also control it in another control region. And the description is also nice. The measurements that we get concern the Pomeron intercept, which you see here. We obtain value of 1.07, which we get from a fit to log Xi distribution using a Regge theory inspired formula. We also measure the T distribution and fit the exponential slope of this distribution, and we get value of 7.6 inverse GeV squared. Both these values are in rough agreement with what is being used in different tunes of Pythia, which we were using for estimating detector effects. We also measured the rapidity gap distribution and the integrated cross-section. So you can see that the rapidity gap that we get is the shape is nicely described by different Monte Carlo generators, but the overall normalization largely disagrees. And you can see it also in the table where you can see compared fiducial cross-section and the cross-section extrapolated to the full T range, and you see big disagreements. So there is clearly some improvement needed in our understanding of the normalization of these cross-sections. The second measurement that I want to discuss is about distributions that are sensitive to underlying event. And these distributions we measured in events containing Z boson. The motivation is presented here on slide 12. It is coming from the fact that hadrons are complicated particles with very complicated internal structure, and so when we collide two of these, the event is also has a quite complex structure involving different effects, also non-perturbative ones. There is also no really a clear separation between hard and soft processes here. So this all is understood presently in terms of phenomenological models implemented in MC generators, and these models need tuning to really describe the data. So the goal of this study is to provide some data that can be used for tuning. So we measured, for each event, we defined a transverse plane with respect to the direction of the Z boson, where Z was decaying into gamma-gamma. We divided into toward region, away region, and transverse regions. In addition, these transverse regions were, one of them was called transmean, the other one transmax, based on the sum of PT that was produced in these regions. And there were 4 observables that we measured: the number of charged particles in each region, PT of charged particles, sum of PT, and mean PT. The measurements was done as I said, in different regions, also in different beams of transverse momentum of the Z boson. and in different means of transverse thrust, when transverse thrust defines the overall shape of the event and is defined here. So on slide 14, you can see examples of different distributions, transverse momentum, number of particles, sum of PT and mean PT. If you look at these plots, you can see that none of them is described by none of the Monte Carlo generators that we looked at. So this clearly shows that that there is a need for better tuning and better understanding of these processes in our present generators. These plots here show you what is the difference between the two transverse regions that we distinguish, the transmax and transmean. And you see that actually the difference is quite large. And this difference is coming from the fact that when we produce a Z boson with a large transverse momentum, there is always a recoil jet. And this recoil jet can also be partly present in the transverse region. And of course, when we distinguish two transverse regions, the one with less activity is less susceptible to these effects. And the plot here on the right shows you the dependence on the transverse thrust with activity, higher activity in low thrust events. Please also take a look that we made all these measurements as a function of transverse momentum of PT of the Z, and we see this characteristic flattening of activity as a function of PT. The last plots that I want to show today, they present differential distributions of all these observables in different bins of different variables. So here in the top row, you can see low PT of Z and distributions of PT of charged particles. Here is the bottom row, high PT of events of the Z boson, and left column is low thrust event. Right column is high thrust event. So this all can be used for tuning. And my last summary slide, I want to mention only that if you are interested in forward proton tagging, there are also 3 very interesting additional talks from Atlas regarding a different detector, which is called Atlas Forward Proton, which can be used for measuring gamma-gamma processes. And we have 2 technical talks. And later today, we also have a physics talk where we show how this can be used for photon fusion measurement processes in Atlas. So that's all from me. Thank you very much.
Thank you, Rafał. Thank you for this nice talk. Do you have a question? I don't see any. Maybe I have a question concerning this large discrepancy in the normalization for diffractive processes. Are there some understanding where this may come from?
I am personally not aware of a good reason for this discrepancy. It is possible that maybe the models that are implemented in PyThiat, which we use as comparison, are not the most sophisticated ones on the market. So I think this is now a role for theorists to try to compare to more sophisticated models and see if they get an agreement or not.
Okay, thank you. I hope theorists are listening to us. Thank you very much.
Thank you very
Rafał. Much. And we will move on. Our next speaker is Rafał Sikora from STAR, who will be talking about central exclusive production of charged particle pairs in proton-proton collisions. Yeah, we see your slides. Please go ahead.
Okay, can you hear me?
Yeah.
Okay, thank you. Hello, everyone. I would like to give a talk on behalf of the STAR collaboration on the measurement of the central exclusive production of charged particle pairs in PP collisions at 200 GeV with the STAR detector at RIC. All materials that I am going to present has been recently published in the Journal of High Energy Physics. A brief introduction to the process. So we talk about the central exclusive production if the 2 beam particles remain intact after the collision or eventually get excited. You can see it marked with red, while the fraction of their inner energy is transformed into the central state, which is here marked green with X. And the central state is separated with the outgoing beam particles or the remnants with the so-called rapidity or pseudo-rapidity gaps. In general, the process can proceed threefold: through double photon exchange, through photo production, or through double Pomeron exchange, with the last being the dominant at the RIC energies. What makes this measurement made by STAR particularly important and interesting is the fact that all particles have been measured, so also the forward scattered protons in the Raman pot detectors. The process is topologically simple because here I'm talking about the production of H plus A minus pair, but it's complex and hard to be theoretically described. At lowest QCD order, the Pomeron has a representation of a pair of gluons, which makes it the double Pomeron exchange suitable for the glue ball production. Here, where the low masses are produced, there is no hard scale and PQCD cannot be applied. In addition to this, there are absorption effects which suppress the cross-section. So there are some additional soft rescatterings which may produce additional particles which fill the gaps. Not only this, but for the two pair hadron pair production, we can have either continuum production or production of a resonance that decays to the pair of hadrons, and the two amplitudes can interfere, leading to some structures in the cross sections. At the time of preparing the paper, there were two phenomenological models of the continuum implemented in the generators. These are DIME and GenX. Also, Pythia has the minimum bias Rockefeller model, which was tuned to CDF data. So we decided to compare our data with these three predictions from the Monte Carlo generators: DIME, GenX, and Pythia. I will only remind you, these are only continuum models and they do not contain resonances that also show up in the spectra. The STAR data that was used in this measurement was collected during several week period in the regular runs with the average pileup between 0.2 to 0.9. In the offline selection, we require two opposite charge tracks in the time projection chamber of the transverse momentum greater than 0.2 GeV and pseudo rapidity less than 0.7 on absolute value. And we require two forward-going protons in the Raman pots, one on each side of the star central detector, in the fiducial region, which is marked in the top right plot with the black envelopes. In the bottom plot, you can see the T's of those protons within the fiducial region, and you clearly see that the distribution starts at 0.04 GeV squared, which means that we basically cut off the photoproduction contributions. Because we measure all four particles involved in the process, we can define the transverse missing momentum, which we require to be consistent with 0 within the 2.5 resolutions, which correspond to 75 MeV. And we have additional cuts which are intended to increase purity of our sample and stay to leave us in the region of high identification efficiency, because we can we measured not only pi plus, pi minus, but also we identified K plus, K minus pairs and PP bar pairs. So here are plots demonstrating our particle identification capabilities. In the top row, we show the chi-squared DDX, which is a measure of compatibility with a given hypothesis. It was calculated based on the DEDX measured for each of two centrally produced tracks. As not only this, we have used the time of flight measurement to reconstruct the squared mass of a particle, and the squared mass of particles are shown in the bottom plots. You can generally see that the Monte Carlo predictions for all these three species nicely describe our data, which demonstrate high purity. And we have numerically, it is less than 1% of misidentifications for pi plus and PP bars, and less than 3% for K plus, K minus. So we really have a good particle identification. Regarding the non-exclusive background, we can generally define three ingredients to this non-exclusive background. The two main come from the central diffraction process. So the process where with the same topology, except that in addition to the oppositely charged pair, we have some other particles, either charged or neutral. And the third ingredient to the background is accidental overlap of the pileup events, mainly overlap of the elastic scattering. So this we see in the Raman pods, and some minimum bias process in the central detector. On the left-hand side, you can see the figure demonstrating the transverse momentum, missing momentum for the pi plus pi minus channel. You can see a clear peak of the signal with the red arrow marks the region which we cut. So the right-hand side distribution shows the row counts for those events from the peak as a function of the invariant mass of the 2 pion pair. With this missing transverse momentum, we can determine fully from the data the amount of the background under the signal peak, shown with magenta. And we can do this differentially, as shown on the right-hand side plot. You can see the distribution of the background with the filled magenta histogram. And we do this for all the observable for which we calculate the cross-section. At the end, we have very pure samples of pi plus, pi minus, and k plus, k minus, less than 6% of background. And for PP bar, we also have small backgrounds less than 12%. So the backgrounds are under control. Let me move to the results. So here we show the differential fiducial cross-section as a function of the invariant mass of the 2 pion pair. Regarding the systematic uncertainties, we show them only for a few selected bins. You can see it with the gray boxes because they are very strongly correlated between bins, and they should be understood as allowed collective movement of the entire cross-section upwards or downwards. And since I mentioned the uncertainties, I would like to stress that the uncertainty here is 4 times better compared to the measurement of the double Pomeroy exchange with detection of forward protons that was published before this paper based on the ISR results. So now let me explain the structures which we can see here. The dip around 0.5 GeV is the acceptance effect. Then we have a peak at 1 GeV followed by a sharp drop, which we attribute to F0 980 meson, which interferes with the continuum. Between 1 and 1.5, we see a clear peak that we attribute to F2 1270 resonance. And at 2.2 GeV, we also see a clear resonance structure. Among the continuum predictions that we show here with 3 colors, we generally attribute dimeson to the best described the continuum. And please take into account that Pythia here is scaled by factor 0.25 to make the visual comparisons easier. So Pythia overestimates the cross-section quite significantly. We have measured not only pi plus, pi minus, but also on the left-hand side, we show the invariant mass cross-section for k plus, k minus on the left, and on the right for a PP bar. On the left-hand side, we can see a peak in the F2 mass region, as well as a peak in the region of F2 prime, 1525, as well as some enhancement in the cross-section in the region of F0, 1710. Regarding the PP bar, the statistics is low. Nevertheless, we can say something about the Pythia, because you can see that even though it's scaled, it's over the data. So Pythia over predicts the cross-section for exclusive PP bar by factor of 8. We use the benefit of reconstructing forward scattered protons. So here we show the differential cross-section as a function of the azimuthal separation of the forward going protons. It is correlated with the delta PT variable that was proposed by Close and Kirk as a global filter. So generally at small dpt, which corresponds to small delta phi, the globals should be enhanced. And what we observe is indeed an enhancement of the cross-section at delta phi less than 90 degrees compared to delta phi greater than 90 degrees. But we attribute it mainly to the absorption, which is presumably stronger at the delta phi greater than 990 degrees. And we can see that DIME, which is only generator that has the absorption included, well describes the shape of the data. And now, side note that the lack of the cross section at delta phi at 90 degrees is due to the fiducial cuts, so the limited acceptance of the Roman pods. So now we have looked into the properties of the central system as a function of the variables that describe the forward system. Here we have the invariant mass cross sections for two delta phi regions. On the left, if the delta phi between forward scattered protons is less than 90 degrees, and on the right hand side, greater than 90 degrees. So the first difference that you can spot is the zero cross section below 0.5 GeV on the right hand side, and it is because of the fiducial cuts. But then you can see that there is a clear difference in the shape, in the magnitude of the structure around 1 GeV. So this structure is more pronounced at delta phi less than 90 degrees compared to delta phi greater than 90 degrees, which suggests that F0 980 is produced more dominantly at this delta phi less than 90 degrees. The same seems to be true for this potential resonance at 2.2 GeV. It's also more pronounced in the left-hand side region. But it is in the situation is the opposite for the F2, which is more pronounced at delta phi greater than 90 degrees compared to delta phi less than 90 degrees. The next variable that we have looked into is the total squared for momentum transferred in the process, so a sum of Mandelstam T's of the two protons. Here we show it separately for the pp bar, for pi plus, pi minus on the left, k plus, k minus in the middle, and pp bar on the right-hand side. Here also we can see that DIME is the best working Monte Carlo generator. Pythia also works fine, except that for the pp bar, Pythia predicts bigger slope than what is observed with the data. Not only this, we have studied the angular distributions in K of exclusive pi plus, pi minus production. So here I demonstrate a azimuthal angle of positively charged pion in a Collins-Soper reference frame in three mass regions. The left-hand side is for masses below 1 GeV, which should be dominated by the continuum production. The middle is for, yes?
Rafał, you are running out of time. So...
Okay, I will speed up. So
okay.
We have three mass regions, and we generally see that in the left-hand side, there is dominant spin 0 production. In the middle, we have dominant spin 2 production, which is consistent with F2 meson that we see. And the right-hand side cannot be described by just one wave, which suggests a mix of the two waves and maybe also higher waves. And we have, at the end, extrapolated the fiducial cross-section to the Lorentz invariant phase space given here with blue. And we have performed a fit of the minimal model containing a continuum of and three resonances. Among those three resonances, we only fixed a mass and width for F2. The remaining two resonances were left free, but we find the two additional resonances consistent with F0 980 and F0 1500. And for the last one, we see that it is enhanced at delta phi less than 45 degrees. So it's kind of correlated with this global filter. So we see enhanced production of this resonance in the region where the globals should be enhanced. And we know from other measurements that this state is considered as potential state with some admixture of gluon content. And we also performed a fit of the exponential function to the different double differential cross-section in T1 and T2. And we see a significant differences of the slopes for different masses and different delta phi regions, which can be connected with different amount of resonances in these regions of phase space that could help theoretical physicists to constrain some PP to meson couplings. And because I'm running out of time, I will probably skip my summary. Thank you.
Thank you very much, Rafał, for this very nice talk and very clean, interesting measurements. One question, Anthony.
Also, thank you for this extremely nice results, because this is for the first time exclusive process. So congratulations, it was always having some admixture, and now it is higher energies and exclusive, which is really great. I want to say only a comment that in principle, we calculate all these resonances with Piotr Lebiedowicz, Otto Nachman in the tensor Pomeron model, and in principle, we can think to make such an analysis because it is crucial, as Rafał said, it is crucial to have these resonances because they do interfere with continuum, and Monte Carlo has only continuum. End of my comment.
Thank you.
Okay, thank you. Thank you again, Rafał. Very nice. And our next speaker is Anna Cicek, talking about exclusive and semi-exclusive production of vector mesons in proto-proton collisions with electromagnetic dissociation of protons. We see your slides.
Okay, welcome everybody. My name is Anna Cicek, and today I will be talking about exclusive production of vector meson in proton-proton collisions and semi-exclusive production with electromagnetic proton dissociation. This subject, which I will be presenting today, was studied in collaboration with Wolfgang Schäfer and Antoni Szczurek. For exclusive production, first we calculate amplitude for photoproduction in photon-proton collisions. And this process in photon-proton collisions was studied at HERA. And next, this amplitude was used to predict the cross-section in proton-proton collisions, and this process was studied at LHC. Exclusive, we calculate separately the photon-pomeron and pomeron-photon contributions and the cross-section as a sum of these two components. For photon-proton collisions, the full amplitude includes real and imaginary part. Rho is a ratio of real to imaginary part of the amplitude, and B is a slope parameter depends on energy. The imaginary part of the amplitude includes two important ingredients, unintegrated gluon distribution functions and the quark, anti-quark wave function of produced vector mesons. In our calculation, we use different model of unintegrated gluon distribution function, and we used two different types model of the wave function of the vector meson. Gaussian and Coulomb. And Gauss wave function better describe data, experimental data than Coulomb. How we choose parameters of the wave function of the vector meson. First, we choose parameters and we calculate the GV, leptonic decay constants, and when we have GV, we can get a decay electronic wave. And when we choose the decay electronic wave in such way that is the same like as experimental values. When we have amplitude, we can calculate cross-section. And here I present total results for total cross-section for phi meson in the left panel and for J psi meson in the right panel. And this total cross-section as a function for energy, as a function of energy. And how I said before, we calculate different model of unintegrated gluon distribution functions. And here I present results for Gauss wave function because how I said before, Gauss wave function better describe data than Coulomb. Our results are compared with HERA experimental data. And now I'm going to the proton-proton collisions. Here I'm presenting the formula for the full amplitude. The full amplitude include the Born amplitude without absorption and the absorptive correction to the amplitude. S is in the elastic matrix of proton-proton in the initial state, and Tk is proportional to the scattering amplitude of proton-proton. And how I said before, in photon-proton collisions, amplitude for photon-proton collision was used to predict the amplitude in proton-proton collisions, and here we have amplitude for photon-proton. And when we have amplitude, we can calculate cross-section. And here I present results for rapidity distribution for J-psi meson in the left panel, and for upsilon meson in the right panel. For upsilon meson, I have different values of slope parameters. The results are for energy 7 TeV, Kutak-Stachta nonlinear unintegrated gluon distribution, and Gaussian wave function. And more results for exclusive production can be found in our previous paper for J-psi, but also for upsilon, rho, or phi meson. And now I'm going to semi-exclusive production with electromagnetic dissociation. To calculate electromagnetic dissociation, we used parametrization of the proton structure function, which are used to drive an inelastic photon flux. The semi-exclusive mechanism can be not completely removed by requirement of rapidity veto. For semi-exclusive production for J-psi meson, we calculate also another mechanism, diffractive partonic and diffractive resonance. And resonance excitation is important for very low excited masses. And these results can be found in our previous paper for exclusive, for semi-exclusive production. Electromagnetic dissociation is of the same size as strong diffractive dissociation. It even dominates in some regions of the phase space. Cross-section for semi-exclusive production with electromagnetic dissociation can be calculated in such a way where Z is the fraction of the proton's longitudinal momenta, P is transverse momentum of the vector mesons, Q is transverse momentum of the outgoing hadronic system related with excitation, and F is inelastic flux photon. Electromagnetic dissociation of protons is calculated using an inelastic unintegrated photon flux. We've calculated based on the model parametrization of deep inelastic proton structure function. The function of structure of protons depends on X-Bjorken and photons virtuality. We calculate for different model, we have calculation for cross-section for different model of unintegrated of structure function of protons. For example, LLM, FFGLM, or SU. And now I'm going to the results. Now I present results for semi-exclusive production with electromagnetic dissociation in rapidity distribution for free vector meson, meson phi, the left panels, meson J psi middle panels, and meson upsilon right panels for energy 7 TeV and for energy 13 TeV. For missing mass, the cut is 10 GeV. And here we have results for different structure function of protons. More results can be found in our last paper for semi-exclusive production of a vector meson. And here I have the same results, but in transverse momentum distributions, also for free vector meson, phi, J psi, and upsilon for energy 7 TeV and 13 TeV. And the cuts of mass is the same, 10 GeV. And now I want to compare exclusive and semi-exclusive production of vector meson. Here I present ratio of electromagnetic dissociation to exclusive production of vector meson in rapidity distribution for different cuts of mass 2, 10, 20, and 50 GeV. These results are for LLAM structure function of protons, and also I have free vector meson phi, J psi, and upsilon, and two different energies, 7 TeV and 13 TeV. We can see that results strongly depends on the parametrization. Here we can see that the results strongly depend on the parametrization of the structure function of photons, and ratio and only middle in ratio depends in rapidity. And now I want to show you the ratio of electromagnetic dissociation also to exclusive production, but in transverse momentum distribution, also for free different vector meson phi, J psi, and upsilon for energy 7 TeV and 13 TeV. And also the cuts for mass are the same, 2, 10, 20, and 50 GeV. And the electromagnetic dissociation gives dominant contribution and large transverse momenta of vector meson. Therefore, the ratio of the semi-exclusive to exclusive contributions depends on PT. And they are my conclusion. For exclusive production, we compare our results with HERA data for photon-proton collisions and with LHCb data for proton-proton collisions. The results for exclusive production strongly depends on the model of the wave function and unintegrated gluon distribution function. Gaussian wave function better describe data than Coulomb. Electromagnetic dissociation of protons is calculated using an inelastic unintegrated photon flux, which was calculated based on model parametrization of deep inelastic proton structure function. And the results strongly depend on the parametrization of the structure function, which we use. And the ratio of the semi-exclusive to purely exclusive contribution strongly depends on the vector of the transverse momentum of vector meson and only midly on rapidity. Thank you for your attention.
Thank you very much, Anna. It's a very nice talk. Thanks for all the predictions. Other questions? If not, I think I thank you again, Anna.
Thank you.
And our next talk is experimental about the measurement of raw photo production at Hera, and the speaker is Arthur Bolt.
Yeah.
Hi.
Hi. Can you see my slides?
Yeah, very well.
Good. Then on behalf of the H1 collaboration, I would like to present to you a measurement of the exclusive raw photo production at Hera. So after a short introduction, I will first present or talk about PyPy photo production at Hera and how we can extract the raw photo production cross-sections from the PyPy measurement. And I will then present kinematic distributions of the raw cross-section that we measure. And as a final result, I will discuss how we can use our measurements to extract the leading redshift trajectory. The analysis has been submitted to EVJC, and you can find a preprint under this archive number. So the first slide, so vector meson production is basically you have an interaction between a photon and a proton that produces a vector meson in the final state. So this is a phenomenon of this strong interaction, and in particular, you can use this to study soft diffraction. So in the redshift picture, soft diffraction is basically governed by the exchange of regions in the low energy regime and the Pomeroy in the high energy regime. And because you have no exchange of color between the two scattering centers, one experimental signature is that you have these large rapidity gaps in the outgoing particles. In the shown example, this would be between X and Y. The characteristics or one characteristic of these diffractive scattering events is that if you look at cross sections, in the high energy limit, they tend to rise with the energy W to some power delta. And in this redshift theory, delta is really related to the redshift trajectories in the way that is given by the formula. The other characteristic is if you look at the momentum transfer distributions, the momentum transfer is given by T, and we look at it at the proton vertex, you typically have very steeply falling or exponentially falling cross-section distributions. In the figure, an overview of photo production cross-section is shown for various vector mesons as a function of the scattering energy W. And for the light vector mesons in particular that you see with the high cross-sections, the high energy dependence of the cross-section is really governed by this Pomeroy exchange. So we can study photo production of vector mesons at the Hera electron-proton collider that was operated here in Hamburg until 2007. And it had, in particular, a center of mass energy of 320 GeV. At Hera, there were two large collider experiments, H1 and SUS. There were just general multipurpose detectors with, in particular, very good colorimetry covering the full solid angle. For this analysis, it's relevant that the good tracking was only available in the central region. And also, there were dedicated forward detectors that one could use to analyze the scattered proton system. Now we want to study photo production of raw mesons at Hera, or with the H1 detector, and the raw meson decays predominantly into a pair of charged pions. So what we need to study is PyPy photo production. Now, to study photo production at the electron collider, what we do is we go to very small photon virtuality, so that the photon emitted by the electron is quasi-real. And then we basically have this photo production process that I discussed before. Now, two things are very important. So because we only study the PyPy final state, there's irreducible backgrounds from other processes that also result in the same final state. So for example, we can replace the rho meson by other vector mesons, omega or a prime. And we also have a large non-resonant channel where PyPy is produced continuously. And in particular, all these processes can interfere with one another. The other thing that we need to consider is, in particular, if you want to interpret our data, we need to separate elastic scattering from these proton dissociative events that were also discussed already in some of the previous talks. Now, how does PyPy photo production look in the H1 detector? So basically, in the photo production regime, the electron is scattered on a very small angle, so it leaves the detector undetected in the backward direction. Also, for these soft diffractive events, the proton is scattered in very forward direction, so also the proton leaves the detector undetected through the beam pipe. And all we're left with is two pions in the central part of the detector. Now, the two pions have very small transverse momenta, which means that we cannot really measure them with a colorimeter, but we have to rely solely on tracking. We can do this analysis in H1 because we had a very nice track trigger, the fast track trigger, so we could trigger these events. And now the remaining challenge is that we need to separate the elastic and the proton dissociative events. We can use this by using dedicated detectors in the forward direction of the H1 detector that we can use to tag these proton dissociative events and then later statistically separate them out from the sample. The other challenge is that if you only reconstruct the 2 pions, the system is kinematic, the under constraint, so this deteriorates the resolution. So we need to do a full unfolding, which we will also discuss a bit later. Also, the limited acceptance of the tracker that I mentioned before results in various small but non-negligible backgrounds that can contaminate the data sample. Now, the data sample that we use for the measurement is only a subset of the H1 data sample because of the availability of the trigger, but nonetheless, we have a very large sample with almost 1 million selected PyPy events. What you see on this figure is the control distribution of reconstructed events as a function of the PyPy reconstructed invariant PyPy mass. You very nicely see you have this peak at 770 MeV, so the sample is really dominated by this row resonance. We model our data with a Monte Carlo model that is based on the DFM Monte Carlo generator. In particular, we model the full PyPy signal, including the row and other contributions. And we consider various backgrounds, for example, from omega, phi, rho prime, and photon dissociation. So I really want to stress that at this point, everything that decays into a PyPy exclusive PyPy final state is considered signal, and only like reducible backgrounds with other particles in the final state are here considered as background. For the proton dissociation, we also use the DFM generator that basically takes measured dissociative distribution, and the Monte Carlo is tuned to describe these measured distributions. Now we come to the cross-section measurement. So as I said, because we have these backgrounds and because we want to separate the elastic from the proton dissociative component, and because we have a limited detector efficiency and resolution, we do a full unfolding. In particular, the unfolding is done with a regularized template fit using the T-unfold package. And in particular, we have several detector level control regions where we employ these forward detectors to kind of have control regions for proton dissociative and elastic scattering that we can use to statistically determine the fractions of events in these channels. And then this allows us to measure the elastic and proton dissociative cross sections independently. The phase space of the measurement is given in the right table. So in particular, in the energy, we go from 20 to 80 GeV. T is below 1.5 GeV squared. Q squared is below 2.5 GeV squared. And for the proton dissociative component, we go up to a mass of 10 GeV. Now we want to measure photo production cross section. So the cross section calculation is just the regular one where you like divide the number of unfolded events by the integrated luminosity. And in order to calculate the photo production from the electron production cross sections, we normalize all of this by the effective photon flux. So this is calculated using the Weizsäcker-Williams approximation. And then we extrapolate to Q squared equal to 0 using the VDM approach. So we really have real photo production cross sections. The first result is shown here. So it's a differential cross section as a function of the m pi pi mass. And now we have separated in red the elastic component and in green the proton associated component. Again, we see we have this rho peak, but now on this logarithmic scale, we also see if you go to higher masses, there's a second rho prime resonance. In the table, this is basically just the fiducial cross section that we get in the phase space together with this split up of the systematic uncertainty. Because of time, I don't want to go into detail here, but just most of the uncertainties we have are really normalization uncertainties. Now, how do we get the rho cross-section from the PyPy cross-sections? For this, we use a Söding model. The model basically models a rho contribution, omega contribution, and non-resonant contribution. They are added at the amplitude level so that interference effects are taken into account in the model. And we can use basically then the model to fit the model to the data and extract the rho component to calculate the rho cross-section. The model is illustrated in the plot as a function of m pi pi. So in blue, we have the rho contribution, in purple, the omega contribution, and in orange, the non-resonant continuum contribution. We add them all up, and you see there's a very large interference that gives rise to this famous skewing of the rho resonance peak here in black towards lower masses. Now, on slide number 9, I show a fit of the Söding model to our data. The model describes the data really very nicely. And you see here the black curves are the fitted model compared to the data points that we saw before. And because the model does not take into account this rho prime second resonance peak that we saw before, we only performed the fit in this limited analysis range from 0.6 to 1 GeV. One nice feature about our data is because we do this unfolding, we can really see for the first time in rho photo production at Hera this omega contribution, which gives this steep edge on top of the rho peak. We can, of course, from this fit extract some physical parameters, which are given here for the mass and width of the rho and the mass of the omega meson, and compare them to the PEG values. So these are all quite consistent. Now we want to, of course, extract kinematic row cross-section distributions. So in order to do this, we unfold the pi mass spectrums in various kinematic bins. So we consider one-dimensional distributions where we have 9 and 6 energy bins for the elastic and proton-associated contribution, for example. But then we also have 2-dimensional distributions where we have 4 times 7 energy and T bins for the elastic and 4 times 5 energy and T bins for the proton-associative component. And this is what you see on these 2 panels here. And then we again take the Serding model, fit it to all mass distributions simultaneously. Then we have to make some additional assumptions on the kinematic parameter dependencies in order to reduce our number of fit parameters. And then we can integrate out the row contribution and get kinematic row cross-section distributions. The first distribution I want to present is the energy dependence of the row cross-section, which is shown here, again in red for the elastic and green for the proton-associative component. And the elastic component is compared to data or to measurement from previous experiments. We fixed target experiments at low energy and then previous HERA and LHC measurements in the high energy regime. We can parameterize our data in form of fit of this power law, where the extracted parameters are given here. So one thing that is peculiar is that while the elastic cross-section indeed rises with energy as expected, the proton-dissociative cross-section falls with energy. However, for a proper interpretation, one has to take into account that the proton-dissociative phase space is restricted quite strongly. So we only go up to 10 GeV in the dissociative mass. And this really strongly shapes the energy dependence of the cross-section. The other thing that we can do is we can take this Donaghey-Lanzow model and describe the full data where we have a region contribution at low energy and then the permanent contribution at high energy to describe the full energy range that is shown in the plot. And also here, the parameters that we get from the fit are given here. Now, one important thing to notice is that if we only fit our data, the parameter that we get is not really the parameter for the Pomeron because it's a bit lower than when we also consider region contributions, which indicates that there still might be some region contributions in the considered energy range. And from the fit, they are estimated at 2% in the center of our phase space at 40 GeV. So this is important for the interpretation of later results. On slide 12, the other thing we can do is we can also study the T-dependence of the cross-section, which is shown again for the elastic on the left and for the proton-dissociative on the right. As I said, one expects an exponential behavior. However, we found that there's significant deviation from this exponential towards larger T. So we use this modified parameterization, which transitions towards larger T into a simple power law and describes the data quite nicely. And we can really then model and describe this deviation from the exponential behavior. Again, the parameters are given here. Now, the final and most interesting result is, as I said, as I showed you, we can measure also 2-dimensional cross-section distributions as a function of T and energy. So they are presented on the left 2 plots, the differential cross-section as shown as a function of T, and then stacked on top of another in the 4 considered energy bins for the elastic and proton-dissociative component, respectively. And we can perform a 2-dimensional redshift fit to the data. So the fit model is similar, like a combination of what I discussed before. So for the T-dependence, we use the same parameterization as before. And then we have this explicit Regge energy dependence where the energy goes to some power of a function of the Regge trajectory. Now, the Regge trajectory at small t, they're expected to be linear. However, we chose this slightly more complicated formula, which looks complicated, but it's similar to a Fermi function. So it's very linear if you're at small t, but then it transitions into a more flat behavior and finally saturates or becomes constant if you go to very large T. So all the curves that you see come from this 2D redshift fit. So in the left 2 plots, the fitted cross-section function is compared to the data. And then in order to visualize the redshift trajectory that we're most interested in, what we do is we fit the energy dependence in all the T bins separately with a free fit parameter alpha T. And then you see these fit parameters alpha T as a function of T in the right 2 plots. And the curves you see in there, these are really the curves that we got from the full 2D redshift fit using this parameterization here. Now for the elastic cross-section, we get an intercept of 1.06 for the leading redshift trajectory and a slope of 0.23. And
you are slightly over time.
Oh, yes, I'm done in 1 second. And we see there's some indication of saturation, but it's not really significant. So with this, I come to the summary. So just one last remark that I want to make is that the intercept compared to previous measurement, it's a bit low. So normally for the Donaghey-Lanzow, you expect something like 1.08. And the probable explanation is that also, as I said, in the energy range, we have probably some small region contribution, which would lower the intercept. So with this, I'm done. Thank you very much for the attention. If you want to see more, just please look up our paper. Thank you very much.
Okay, Thank you very much for this nice talk, for the nice result. One question, Anthony.
Also, congratulations for a very nice talk and nice results. I mean, you fitted, I just want to refer to your T dependencies. You fitted T dependencies, but I think this change of the slope for larger T may be an indication of some dynamical effect of something like multiple scattering. And this is interesting in this context. Of course, you parameterize it, but it's a question what it means deeper in physics. And my feeling is it may be related to this multiple scattering. So maybe theorists should work, including us.
Yes, we'd be happy to, if you can do that. I mean, I think in the paper we should that we can describe the data and we don't try to interpret
we should do something for this, yes. Thank you.
Okay, thank you, Arthur. The next speaker is Otto Nachtmann. We'll be talking about the central exclusive diffractive production of axial vector mesons. Yeah, we see your slides. Please go ahead. But we don't hear you yet. Are you muted? Hello?
Do you hear me?
Yeah, now we hear you.
Now we hear.
Okay, go ahead.
So, oh, sorry, I'm still, damn. No, how do I'm still have problems with this machine, I'm sorry. Stummschaltung, Video freigeben. How can I
think you might be able to go back in the slides with a right mouse click. Maybe try that.
Right.
Does it go back?
No, it goes forward.
What about keyboard?
Or with the left cursor on the keyboard?
I have no. Sorry. Stummschaltung, Teilnehmer, neue Freigabe, Kommentar, Fernbedienung. No, sorry.
You will probably have to switch to the program that displays the slides and then go left with the cursor.
But I can do nothing at the moment. Maybe.
No, it's okay now. Keep going.
Now it goes. Yeah. All right.
Okay. Very well.
So my talk will be about central exclusive production of axial vector mesons F1 in proton-proton collisions. And this is work done together with Piotr Lebiedowicz, Josef Leutke, Anton Repan, and Antoni Szurek. So it's a Krakow, Vienna, Heidelberg collaboration. So this is outline of my talk. After an introduction, I will talk about the Pomeron-Pomeron F1 coupling, show some preliminary results, and draw some conclusions. So here's the introduction. In this talk, we will be concerned with central exclusive production, CEP, of F1 1285 and F1 1420 mesons in proton-proton collisions. So proton PA, proton PB with momenta go into two protons, P1, P2, and in the middle an F1 meson. At high energies, this should be mainly due to double Pomeron exchange, and I have shown you the figure here. So the protons, they each shake off a Pomeron, and then the Pomeron fuse to give an F1. So the relevant kinematic quantities are standard. I will not go through them. S is the center of mass energy squared. We treat our reaction in the tensor Pomeron approach, which was introduced by Everts, Maniatis, and myself in 2014. And this approach has a good basis from non-perturbative QCD considerations. Now, in this model, the Pomeron and the charge conjugation sequel +1 regions are described as effective rank 2 symmetric tensor exchanges. The Hadron and the sequel -1 regions are described as effective vector exchanges. I should say that a tensor character of the Pomeron is also preferred in holographic QCD, and here are some relevant references. There are by now many applications of our tensor Pomeron model to diffractive processes. We have treated many two-body hadronic reactions, photoproduction reactions, especially also the reaction which Arthur Bolz just talked about. We have got a very nice fit to low X deep inelastic scattering. And we have treated many CEP reactions, these CEP reactions mostly together with Antony Šurek and Piotr Lebiedowicz. So CEP, central exclusive production, proton plus proton, giving proton plus X. And the X's we have looked at are eta, eta prime, so pseudoscalars, F0, F2, proton, antiproton, KK bar, phi, 2 phi's, 4 pi's, and so on. So it would be very nice if star results could be compared to all our theoretical calculations. I think what's really missing are good event generators. So from these studies, we know the form of the effective Pomeron propagator and of the Pomeron PP vertex. So new in our present work is the Pomeron F1 vertex. So the second part, I will discuss this Pomeron F1 coupling. And I will give you a coupling Lagrangian. And from this, in standard way, one gets the vertex function. So here we have two Pomerons giving F1. Now, since we have tensor Pomerons, the Pomerons carry two indices, two Lorentz indices, kappa lambda, rho, sigma. We follow two strategies for constructing this coupling Lagrangian. The first one is a phenomenological approach. So we consider, and in this approach, we consider first the fictitious process, the fusion of two real spin 2 Pomerons of mass m. You can call this also tensor glue balls. And then we ask that they give an F1 meson with spin parity and charge conjugation 1 plus plus. So here's our reaction. M is the mass of the fictitious Pomerons or glue balls, and epsilon 1, epsilon 2 are the polarization tensors. Epsilon is the polarization vector of the F1. So let's work in the rest system of the F1, where the two Pomerons collide head-on to give an F1 at rest. Now we can do a simple angular momentum analysis of this process. The spin of the two real Pomerons can be combined to give a total spin S, which ranges between 0 and 4. And this then has to be combined with the orbital angular momentum L to give J by BC 1 plus plus, the quantum numbers of the F1. Now, there are exactly two possibilities, which we label by angular momentum, orbital angular momentum L and spin LS. It's 2, 2 and 4, 4. And it's easy to write down corresponding coupling Lagrangians. The 2, 2 term looks like as follows. Here are the effective Pomeron fields, P kappa lambda, P rho sigma, with two asymmetric derivatives in between corresponding to L equal 2. And this is sort of the field strength tensor of the F1 meson. U beta is the field of the F1, that's d alpha U beta minus d beta U alpha. Here M0 is introduced for dimensional reasons, it's 1 GeV, and G prime is a dimensionless coupling constant. Gamma 8 is a known tensor function. It looks too complicated for me to showing you here. Now the 4,4 term looks similar. It has now 4 asymmetric derivatives in between corresponding to L equal 4, and again a coupling constant which is dimensionless, and a tensor function which has now 10 indices. Now we use these couplings and supplement them by suitable form factors for treating our CEP central exclusive production reaction. Now the second approach which we follow is coming from holographic QCD, and it uses the Sakai-Sugimoto model. Here are some references to this model. And there, it looks much more sophisticated. The Pomeron-Pomeron F1 coupling can be derived from the bulk Chern-Simons term, requiring consistency of supergravity and the gravitational anomaly. And then this Chern-Simons Lagrangian looks quite different. It has again 2 couplings, kappa prime, dimensionless, and kappa double prime, which has dimension Jeff to the -2. And here you have again the F1 field, the 2 Pomeron fields, and some derivative and epsilon tensor in between. Now, for our fictitious reaction with real Pomerons, there is a strict equivalence. This Chern-Simons Lagrangian is strictly equivalent to the certain sum of the 2,2 and 4,4 Lagrangians. Of course, if the couplings satisfy a certain relation, a certain linear relation, G prime is kappa prime m0 squared over k squared minus kappa double prime m0 squared k squared minus 2m squared over 2k squared, and G double prime is kappa double prime 2m0 fourth over k squared. Now, that is strict equivalence for this real fictitious reaction, for the fictitious reaction, I should say. For the reaction which we are interested, central exclusive production, the Pomerons, of course, are not on a fictitious mass shell, but their mass squared, T1, T2, are less than 0 instead of m squared. But replacing here in this relation 2m squared by T1 plus T2, we expect still approximate equivalence to hold, and this is indeed confirmed by explicit numerical studies. So I come to preliminary results. We have compared our calculations with experimental results from the WA102 experiment. This experiment studied proton-proton collisions at root S 29.1 GeV. And they worked at the omega spectrometer at CERN in the years 1997 to 2000. And they had the big advantage that they could measure the complete final state. So they gave us cross-section and also dependence distributions in T, in the and in an angle phi pp, where phi pp is the azimuthal angle between the transverse momenta of the 2 outgoing protons. Similar angle was discussed by Rafael Sikora in a previous talk. Now, the cross sections which they get also had a cut on the X Feynman of the produced meson of less than 0.2 in absolute value, and the cross sections are around 7,000 nanobarn for the F2 1285 and about 1,500 nanobarn for the F1 1420. So here are results for the T dependence, the momentum distribution. And you see that with the 2-2 term, the L equal 2, S equal 2 term alone, we get a nice description of the T dependence and of this very non-trivial phi angular dependence. And of course, our results depend on a parameter in the form factor, and this parameter, cutoff parameter in form factor, has a reasonable value, 0.7 GeV. This value then comes from fitting the total cross-section. Not only the distribution, but then the total cross-section. I should also say that absorption effects, which are very important in this case, have been included. So we can also fit this WA102 data using the 4,4 term only. In this case, we get a coupling constant in absolute value 10.3. Again, absorption effects are included. If we have only one coupling, then this cross-section, of course, cannot know about the sign of the coupling. Only a relative sign of two couplings can be gotten from experiment. Now, here is the Chern-Simons coupling. And also there we get, I only show you here the phi pp, the angular distribution. We get a corresponding fit to this phi distribution, and the kappa prime is minus 8.8 and the ratio here -1. And if you fit now these numbers into the relation which I showed you, you find that this roughly corresponds, or very rather precisely corresponds to a pure LS44 term. So I'm nearly done. I come to my conclusions. We have discussed in detail the forms of the Pomeron-Pomeron F1 coupling. I think we obtain a good description of the WA102 data at root S 29.1 GeV. And our preliminary results for LHC energies indicate similar distributions as at the lower energy and a cross-section of 2 to 35 microbarn, depending on cuts. Detailed tests of this model are possible, and I think experimental studies of single meson central exclusive production reactions will give many Pomeron-Pomeron meson coupling parameters, and their theoretical calculation is a challenging problem of non-perturbative QCD. I think with this Sakai-Sugimoto model, for instance, one is just at the beginning of such interesting calculations. Thank you very much for your attention.
Thank you. We have a question from Marek.
Yes, very nice talk, Otto.
Thank you.
We heard yesterday that there is some experimental evidence for existence of the Hadron. Can one play this game with Hadron and learn more about it from analogous processes where you have Hadron-Pomeron fusion?
Yes, of course. Yes, of course. We had, I think Piotr talked yesterday about phi and double phi production. These are excellent for studying the Hadron.
No, but what Piotr talked about is slightly different, if I understood correctly. I mean, analogous to what you did.
Yes.
Fusion, instead of Pomeron-Pomeron fusion, Pomeron-Hadron fusion, which will create mesons with different.
Yes, but phi is a very good. Then you have to have C equal -1 meson.
Yeah.
So phi or J psi is very good. Also, two phis are good because you can have then Pomeron, Hadron, Pomeron as exchange. So these are excellent processes for studying the Hadron at LHC. And we have published 2 papers on this, on the single phi and on the double phi.
I see. Thank you.
Very okay, of course.
Okay, so there is another question from Anthony, very quickly.
It is not a question, but because I know Rafa Shikora was probably listening this talk, we kindly ask Atlas and STAR to look at F1 production, then you should look to 4 pion channel. For instance, 4 charge pions.
Okay, so at STAR it would be hard, but at Atlas, yes, some results should be released soon.
So thank you, and we are waiting for those results.
Yes, I mean, for time reasons, I did not mention this. The F1 should show up as a peak, a sharp peak on the background from the 4 pions from the F2. So could be a very nice signal for Atlas.
Okay, thank you for the suggestions. I think, unfortunately, we have to cut the discussion. We don't have more time. Thank you very much. Thank to all speakers. And okay, for the audience, we are running slightly behind the schedule. We will reconvene, we'll shorten the coffee break and reconvene at 11:40. And the speakers for next session, please can they stay connected and check their sharing in the meantime.
Okay, thank you very much.
Yeah, thank you. Just Otto, can you stop sharing so that we can...
stop.
Yeah, thank you.
That's fine.
Thank you very much.
Yeah.
Hi, Sharker. Can you hear me?
Yeah. Hi, Antonio.
Okay. Hi, how are you? So I guess we go through the checks. So hi, Wen Chen, I see you.
Yes. Hi.
Could you share your slides?
Not yet. I will do it immediately.
Okay.
So.
All right, I see them.
Okay, great.
Okay, thanks.
Sure.
So Ilya already checked, right? The sharing.
Right, I checked it.
Okay, good. So Con, I'm sorry, let me know if I'm speaking correctly your name.
My name is...
I can see it.
Yes.
Sure. Okay. Could you share your slides?
Yes. Let me do it. Do you see it?
Yeah. Okay. Looks good.
Okay. Now I can stop sharing.
Thanks. Is Marco connected?
Yes, I'm here. Can you hear me?
Yeah.
Good. I'm trying to share in a second.
Okay.
Is it fine? Can you see the slide? Yes.
Yeah.
Okay.
Thanks.
I can switch also. Thank you.
Okay. Is Jennifer connected?
Yes. Can you hear me?
Yes.
Great. Okay.
Could you share the slides?
Yes, I'm trying. Sorry. Can you see them?
Just a second.
I tried going full screen, which doesn't always work on the Mac.
I just see a message, but not yet.
Okay, let me stop this in 1 minute. Sorry about this. Just a
Or
się dzieje, jesteśmy aktywni w frontach. Co? Bezprzedny. I byłem aktywny i się pojawiałem w naszej pracy.
Rafał wczoraj powiedział, że na staż to jest trudne, ale na Atlasie bardzo.
Na Atlasie?
Zajmują się tym, tak?
Tak.
No dobrze.
Ale to chciałem powiedzieć, to była okazja, żeby powiedzieć.
I see them. Okay, so that Jeff is okay.
Yeah.
So now Denis.
Ale tak,
is it Anton who is speaking?
Nie mamy jakichś informacji. Pokażemy te przewidywania.
Wie pan co, ale my musimy zrobić taką analizę.
Just muting me for a minute. Denis, are you there?
Hello, Antonio. Can you hear
Hi,
me?
Denis. Yes, how are you, Denis?
Very fine, thank you. How are you?
Fine.
Good to see you.
Good to see you too. How could you share your slides for us to check?
Give me just a minute, please.
Yeah, don't worry. All right, I see the window.
Is it okay now?
It's okay. So you do it from the browser?
Yes. I just opened from the browser, but I will download it and then make it.
Okay. Okay, that should be fine.
Okay, thank you.
Thanks. And is Anthony connected? He's the last speaker. I don't see him. Anthony Badea. Still have a minute or so before we start. Let's see. Okay, no. Let's see if he connects during the session. Right. So Shaka, we said 11:40, right? To restart.
Yeah, I think, yeah, that's what we said.
Yeah, so I think we're already on time. So, hello everyone, I'm Antonio Villela Pereira, so I'll be chairing the session. So we start, so this session has several interesting talks on Drauyan, measurements and predictions, jet substructure, and also hadronic event shapes. So we start with Wen-Chen Chang. So I see already your screen share. Ask everyone to please keep to your allocated time. Please do start. Thank you. I'll mute.
Thank you. This is Wen Chen. So in this talk, I will speak on the lepton angle distribution of the Drauyan process and see how the QCD actually played a role inside it. And with this property, we can actually use this for the jets discrimination. So this is the work in collaborate with the Genchi, Evan, and Oleg. So here is a simple cartoon showing the Drauyan is the quark anti-quark anomalous during the hadron collision with the dilepton detected in the final state. The definition of the lepton angle distribution is actually constructed in the hadron plane. We actually get the momentum information of the incident, the hadron, and the beam. So, for example, in the convention of the Collins-Sober frame, we can define the z-axis bisects of this two hadron. And then this theta angle is actually this lepton vector with respect to this z. And then azimuthal phi angle is how the lepton plane separated from the hadron plane. So conventionally, there are two expressions for this angular distribution. The first one is this 1 plus lambda cosine lambda mu nu for the fixed target experiment, and this A0, A1, and N2 for the collider experiment. So in the leading diagram of the Drauyan, which is come from QQ bar annihilation, you can prove that the angular distribution should be 1 plus cosine theta square. that means the lambda is equal to 1 and all of this azimuthal dependence should be gone. That equivalent expression, it would be this A0, A1, and A2 are going to 0. So if for the Z production, actually, we can look into more higher moments that like something like a A3, A4, 5, 6, and 7. For example, here A3 and A4, which is actually characterized in the parity violation coming from the virtual photon interference with the Z. So when the QCD effect is coming, for example, we get this gluon in terms of the virtual correction, or the gluon radiate out in this QQ bar process, or even the quark gluon Compton scattering comes in. So it was in 1978, there's this Lanton relations was proposed, is the lambda was started with this, the QCD effect come in, the lambda will no longer to be 1 and the nu can become non-zero. However, this 1 minus lambda to nu at the first order of the QCD effect is proved to be, should be equal to 0. And equivalent expression is A0 equal to A2. However, in the later on, the fixed target experiment using the pion beam, actually, when people, we can clearly see this azimuthal dependence in terms of the phi for the Joyen process. And we looking into this Lanton relation and find it's clearly been violated at the large PT. So this was something that the first evidence find in the Lanton violation in the fixed target experiment. And then recently from the LHC, so CMS actually first published this very nice, accurate measurement of all of this A0, A1, A2, and A3, A4. In the final plots here, okay, so they clearly show the very strong dependence on the transverse momentum, this QT dependence. And on this plot, it's very clearly to show also the violation of the Lanton, which is the A0 is no longer into the A1. So other than this Lanton violation and the transverse momentum dependence, they also measure the rapidity dependence of all of this AI parameter. So quite interesting, you find that the A0 and the A2, they don't show the very strong rapidity dependence, while A1, A3, and A4, indeed, the rapidity dependence was there. And Atlas also making similar measurements, and the general observation is quite the same. So clearly observation of the Lanton violation at the large PT, and the same as the A1 and A3 show the rapidity dependence. So in general, from all of this Drell-Yan angle distribution, we observe distinct QT dependence, and we find out this Lanton violation, which seems that some effect actually beyond of the first leading order of the QCD effect. We observed the violation both in the fixed target and the collider experiment, and also as well as the rapidity dependence. So here we try to answer two questions. The first one is, can this feature be understood by the PQCD? And the second one is, can we provide any simple picture for the interpretation? So in this paper in the 2017, it's actually performed a state of art, the fixed order PQCD calculation for the comparison with the CMS data on the A0 and A2. So it's from here is actually starting from the alpha S at the first power and move to the second and the third power. And here you can see that with this running out of going up to alpha S third power is actually describe the data rather well. And one interesting observation here, because here on the panel, the bottom panel here is actually using the next leading order calculation result, which is alpha square as a reference. As you can see, this A0 calculation using next leading order or next leading order are actually quite similar. However, the deviation is only C for the A2. So when you go to the higher order calculation, this A2 is actually reduced. So this is some interesting observation from the PQCD calculation. And similar result can also be seen from the comparison with the ATLAS result. And they also a quite nice, very good description of this Lanton violation can be described by, found in the CMS and ATLAS can be described by this fixed order calculation. And in this paper is actually making the claim we have to go to the alpha as the third power in order to give a reasonable description of the ATLAS, the data. So in the recent work we do actually, as we actually only perform the next leading order calculation in this plot for showing the A0 dependence on the QT. And here we overlay the contribution of the QG quark anti-quark term and the quark gluon Compton scattering term. As you will see, the experimental measurement is the weighted average of the contribution from these two processes. So this is actually suggest if the experiment, they will be able to look into the event sample, which is contains Z plus a single jet, they can actually find out the A0 from this single jet event sample could be different from if they will be able to make sure that jet is come from gluon or come from the quark one. So this will be used as a useful property in terms of the jet discrimination. And furthermore, from here, we actually perform the next leading order calculation. So it's actually described the CNS data as well, rather well. And if we only selected out of the event for the Z plus 2 jet, actually it's clearly see that this Lanton violation signal will be enhanced in this kind of example. So such kind of the information, I guess it would be very useful to be wait for the confirmation by the measurement by either CMS or ATLAS. So for the fixed target experiment, we also perform the QCD calculation and try to compare. And over here, in general, it's described the general feature, but quantitatively, actually, it doesn't go through that as well. So for example, this Lanton violation cannot be described at all. Even the signs are different. So here, for example, people already suggest some kind of a non-perturbative TMD Bohr model effect, try to accounting for this Lanton violation in the fixed target, that low QT region. And in the recent work, we also provide some prediction on the coming measurement of the compass using the pion-induced result. So the answer for the question is that the PQC can partially answer describe all of this data. So are we able to have some simple picture for the interpretation? So we did some work and have this suggestion. So when we looking previously, when we're looking into the definition of the angular distribution, we only looking into the Hadron plane and the lepton plane. But fundamentally, if we introduce this the colliding direction of the quark and anti-quark direction, of course, experimentally we are not able to measure it. But we can imagine this kind, if we are able to align this lepton direction with respect to this Z prime we call natural axis, then all of the angular distribution will be most simplified over there. There will is really something like a 1 plus the cosine theta square, 0. Okay. But due to the experimental major constraint, we can only access the information through the Hadron plane and the lepton plane. So in that sense, we have to express this theta 0 by the experimental measured theta and the phi. So then that means we have to make in some mathematical transformation. That was the will be related is how the angle dependence between z and the z experimental defined z and this intrinsic z plane, as well as the so-called quark plane with the Hadron plane. So after plugging this mathematical expression, it's look like a little bit complicated. But if you making a mapping with the experimental expression, actually you can convince yourself all of this A0 parameter, they are actually the event average of all of this microscopic theta 1 and the phi 1, which is introduced on the previous slide. So based on these things, actually there will be on the first order alpha s, if you consider only one single gluon radiation from QQ bar or quark gluon Compton scattering, this phi 1, that means the quark plane and the quark plane will be completely coincide with the Hadron plane. This phi 1 was actually either 0 and pi. That would be very naturally explain why as the leading order A0 and the A2 are actually the same. When we move to the higher order, like a 2 gluon radiates from 2 separate quark lines, they were making this phi 1 to be non-zero. And in that case, this A2 will be less than A0. And it's also, that's what we observe from the experiment. So other than this, we can also consider the similar property for the A0, A3, and A4. And we will see there will be some cancellation effect happen for them, and they can describe why we observe the rapidity dependence for them. So here comes the summary. The PQCD calculation and can really quantitatively describe the Drell-Yan angle distribution from the collider. There is some deviation in the fixed target data. And the Z plus jets angle distribution can be used for the jets discrimination. And when we introduce this geometrical picture of the natural axis, we can actually describe quite an interesting feature we observe in the angle distribution. So this is the reference. And thanks for your attention.
Thanks a lot for this very nice talk. So we have one question by Anton.
Hello.
Yes.
My question is a little bit political. I mean, because there's your interpretation in terms of transverse momentum, this could be probably quantitatively addressed in KT factorization approaches. I am not sure this is what you mean. But my question is, what is your opinion? You think this effect cannot be explained in collinear perturbative QCD?
Yeah, so all of this calculation was actually done by collinear PQCD calculation. So there is no KT factorization and also no resummation effect is considered.
I see. So you think it can be understood within collinear approach?
At least at a large PT from the collider, that is very clear. But for the fixed target one, it's still, since we didn't perform the resummation one, so we cannot make in the claim.
Okay, thank you.
Thank you.
So this is Ilya Gorbanov. Can I ask a question?
Yeah, please go ahead.
Can you go back to slide number 12? When describing the slide, you said that you can use this information to better discriminate between quarks and gluon. jets in experiments. Can you be a little bit more precise on how you suggest to use it for discrimination for such?
Right. So thank you for your question. So this kind of a discrimination is probably difficult to be done on an event by event basis. But in our thinking is, suppose right now experimentally people propose some kind of the way to separate the gluon jet and the quark jet. For example, if this quark gluon Compton scattering, so the radiate one should be the quark jet, and for this QQ bar should be the gluon jet. Suppose they experimentally already proposed some of the way for this jet discrimination, and they use in this way and apply to the real data, and they can characterize their event sample. Then what we propose is actually they can look into this angular distribution of the event sample and try to look into their A0 distribution to see whether they actually can be described by this prediction by the PQCD curve. That is what we mean here. And in that sense, that can give in the support or confirmation about this experimental way of characterizing the jet discrimination.
Thank you. And one more question, if possible. In one of the last slides, you said that in this geometrical approach, you're expecting to have A0 and A2 Lamtung relation to be true for the cases with 0 and 2 and 1 associated jet. But when having 2 associated jets, you're expecting it to be violated. In this sense, can you give some guidance on the choice of the axis, z-axis in the experiment to prove this statement?
There is no specific, experimentally, you can only define this z. You will be able to construct this z prime. So z, you still follow this construction of the Collins-Sober using the beam and the target momentum direction. So the point is actually, if you experimentally, you will be able to characterize the event with the 2 jets in the final state. Then you're looking into this the Lantong by this A0 and A2. So our based on our thinking, this effect will be enhanced. Actually, based on PQCD is over there, because right now the experimental measurement is the inclusive one. So in some sense, this Lantong violation signal is a little bit diluted. That is the message we want to say.
Thank you very much.
Okay. Thanks again, Wenchen.
You're welcome.
Move on. Thanks again. So we can now go to Ilya Gorbunov. Could you share your slides, please? So Ilya will talk about area measurements with the CMS experiment. So please start when you're ready.
Hello. So I will. So why is it why the Drell-Yan measurements important? First of all, by carrying out Drell-Yan measurements, we can test standard model, we can constrain partner distribution functions, extract parameters such as sine squared, theta Weinberg, forward-backward asymmetry, angular coefficients, and others. We can evaluate an important source of background for many beyond third model physics. We can test different Monte Carlo models and test production mechanism dynamics. More than that, it is a precision measurement with a Hadron Collider. So, a few words about Brilliant process. The production of lepton pairs is well known, and theoretical calculations are well established up to next to leading order. And comparison of data in Monte Carlo provide a strengthening test of QCD and can significantly constrain PDFs, and Brilliant is a major background for TT bar and dye boson measurement as well for many new physics. So, what are the new 13 TV results by the CMS? First of all, it's the 13 TV results for the Brilliant differential invariant mass cross section. Those measurements were carried out at 13 TV using 2.8 inverse femtobarns of 2015 data. In the mass range of from 15 to 3000 GVs. The measurements were compared to different theoretical predictions, namely MATGRAPH and FUSE. And the results are now public, and all the links in the talk are clickable. Then I would like to mention the 13 TV results for the Z production cross sections. There are differential PT, phi star, and rapidity cross sections as well, which are available both for electron muon and combined electron plus muon channels. As well as the cross sections. Then I would like to say a few words about the angular coefficients. So here is the Collins-Soper frame, which was used for to measure angular coefficients with the CMS experiment. The cosine theta phi differential cross section was which was used for the measurement with the CMS experiment is the following one. If this expression is integrated over phi star, one can derive the expression for the forward-backward asymmetry. And here are the results for the angular coefficients at 8 TV, which were derived using 19.7 inverse femtobarns of data. One can see that there are some strong dependencies, rapidity dependencies for some of the coefficients, and there is a clear Lambton relation violation. Here are some details on the coefficients and the dependencies on the underlying physics parameters. And those measurements can be further extended by measuring coefficients outside of the Z-peak, introducing additional coefficients, and trying to measure quark gluon and quark antiquark production mechanisms separately. Then here are the ATV results for the forward-backward asymmetry, and here are the cosine theta cosine theta distribution for two invariant mass regions for Z to mu mu and Z to E for dimuon and dielectron final states. The top one is the left hand side plots are for low invariant mass region of 50 to 60 GeV, and the right one is for the high invariant mass region of 130 to 150 GeVs. And one can see that for the high invariant mass region, the distribution is asymmetric. And this is because of the forward-backward asymmetry, which is shown on the next slide. Here is the result of the forward-backward asymmetry measured at CMS at 8 GeV with 19 inverse femtobarns of data. These are the combined results in the electron and muon channels. The measurement is separated in rapidity beams to suppress dilution, as dilution is larger for the low rapidity region and decreases at high rapidity regions, while the acceptance has the opposite effect. And here is the unfolded AFB distribution for the rapidity region from 2.4 to 5 with the ATV for the electron channel separately. There are also weak mixing angle measurements available with the CMS experiment. Those measurements use the AFB, and they rely on the fit of experimental AFB distribution with theory at next to leading order. The statistic, for this measurement, 19 inverse femtobarns of data was used, and the statistical and systematical uncertainties were significantly reduced with respect to 7TV analysis. This are one of the most precise measurements, although there are still combined lab plus SLD results which have better precision, but hopefully with the high luminosity LHC and the upgrade of the CMS, one can get even more precise measurement, and those estimations are described in the table below, and more details are available on the paper in the note listed on the slide. To conclude, I would like to say that high precision measurement, including weak mixing angle, are available and carried out with the CMS experiment. Some channels are analyzed at 13 TV, including the Z cross-section, Brilliant differential invariant mass cross-section. And the others, the standard model predictions are testing, including weak mixing angle, asymmetry, forward-backward asymmetry, Drell-Yan angular coefficients, Lambton relation, and the others. And these measurements provide invaluable constraining power on PDFs, in particular PDFs. Thank you for your attention.
Thanks a lot for this very nice talk, Ilya. I see a question by Xingu Li. Please go ahead.
Yes, so can you go to page 4? So do you know which PDF set you're using here?
It's NLO PDF version 3 PDF set.
Okay, did you know? Okay, then so page 11, I don't quite understand how CMS can reach rapidity greater than 2.4.
This is this measurement is done with the ICHEP Hadron forward calorimeter of the CMS, which is outside of the tracker acceptance, and which but still can be used to extract to measure AFB.
Okay, interesting. Thanks.
There are large there are some systematic uncertainties, and there are large corrections applied to these measurements, but still we believe it is very valuable, being of large being done in larger rapidity region where the dilution effect are significantly reduced.
Okay, thanks.
You're welcome.
Okay, so I have time for just another quick question, if there is. If not, thanks again, Ilya. The next speaker is Qing Wang. She talk about DRAM production at NLO, the Parton Bridge method. Okay, I see your slides.
Okay.
Please start whenever you're ready. Thanks.
Thank you for the nice chance to present the DRAM production in Parton branching method at low and high DRAM Mars. So I will quickly introduce the TMD and Parton branching method and focus on its application in the DRAM production. So the TMD, it is the transverse momentum dependent Parton distributions. The transverse momentum effects are naturally coming from the intrinsic KT and the Parton shower. And with this new approach, Parton branching method, one can determine the integrated PDF from the Parton branching solution of evolution equation. And it could cover all the transverse momentum from the small KT to large KT, as well as a large range in X and mu squared. And so it's a novel method to solve evolution equations. And besides, it could also determine the TMDs. Since each branching is generated explicitly, energy momentum conservation is fulfilled and the transverse momentum distributions can be obtained. So, and as for the fit, we use the X filter and use the data from the Hadron. And more details you can find in Saha's talk on Tuesday. And the nice thing of it is it can be easily extended to include any other measurement for the fit. So here I just show two TMD distributions. One is the left is for the up quark and the right is gluon at the energy scale 100 GeV with small x like 0.01. In the plot, there are two curves represent two different sets. One is PT ordering and another is angular ordering. And we could see that the difference of these two different sets are essentially only in the low KT region. As for the uncertainty, the experimental and model uncertainty are obtained from the fit, which is quite small. And at the low KT, the uncertainty from the intrinsic KT is sizable. So now we move to the applications. So from now on, the prediction I'm talking about is with MC at NLO with TMD. So we use MC at NLO to generate the hard process, while the soft and the collinear parts from the next leading order are subtracted. And then we add it back by TMD. So, and we call it MC at NLO with pattern branching. And we could see in the plot that we compare the prediction with the measurement of the dry-in at ATV. And the data is from, the black point is data and is from Atlas. The blue and the red curve are the PBTMDs. And if you look at the ratio between the prediction and data, we could see that the TMD with AMC at NLO describe the low QT region very well and with very small uncertainties, while the scale uncertainty is sizable, but it's coming from the hard process. And you may notice in the plot that at large QT, like the prediction is a little like underestimated the data because we miss the contribution from high order. And here from the pink curve, which is the dry-in plus one jet, and we could see if we just add it, if this could contribute for the high PT of the dry-in. And more details actually is covered in Armando's talk. So, and here I just cite one plot from him. So if we add the dry-in with high order, we could see like the high PT region is much better, which is the blue curve in the small figure below. And next slide. So we also compare the predictions with the dry-in at a certain TV with the data from CMS. And besides the TMD, they also compared with other predictions as Response or Geneva. And we could see that at the low PT region, the TMD provide very good description, while at the large region, like we need a high order matrix element. And this is already correct because now we managed to add high order now. And the uncertainty in the pattern branching method is mainly from the scale of the matrix element. So besides, we also look at the low mass and the low energy scale. And at the low mass, there is very little room for the QCD evolution. And the PT of the dry-in is dominated by the intrinsic KT and the soft gluons, which need to be resumed. And so we try to compare it with the latest measurement from Phoenix at energy scale 200 GeV and the low dry-in mass around 5 GeV. And two other older measurements are also compared at the energy scale, the 62 or 38 GeV. So we were wondering if the pattern branching method with AMCLTO can apply on the small energy scale. Because last year there was a paper to declare that there is a small PT crisis. So we were wondering if we could do it. On this slide, so we compared the predictions with these three measurements at different energy scale. And so the blue-red curve are the PBTMDs with the band represents the different uncertainties. And we could see the mass distribution is well described by the PBTMDs. And if we look just at the first plot, there is one more prediction is an NPDF, the blue curve. And it looks slightly better because they have more like PDF to fit the constraint. So we could conclude that it's It's sensitive only to the collinear PDF. And at the smallest energy scale, a large X can be approved by path branching method. But the PDFs, since we use only fit to the higher data, so it is not well constrained at the large X. And next slide. So we are looking at the dry EM-PT spectrum in these 3 experiments. And for the Mars, it's around 5 GeV. And we could see that in a PT range less than 5 GeV, the measurement is with very good. The PT spectrum is well described by the pattern branching method.
Oh, Quinn, are you there? Seems. Hello, Quinn. Can you hear me?
Yes, I can hear you.
It seems I lost your audio for a minute or so.
So excuse me.
But now it's okay. Yeah, 12.
Okay. Okay.
Okay, go ahead. Now I hear you. Go ahead. Sorry.
So I just so on the 12 is the PT spectrum of dry EM compared with these 3 measurements. I mean, could see that the dry EM PT spectrum is well described by the pattern branching TMDs, and we do not see these small PT crises, which I cited in the backup. And very good agreement within the uncertainty and with very small chi-square is 1.27. So now I think we can go to the conclusion. So for the application in the dry EM from the pattern branching TMD, the dry EM QT spectrum can be improved without new parameters, and it agrees well with the result from LHC at a low PT region. And the dry EM QT spectrum at low mass and low energy scale is also well described by the PBTMD. And we could see it's a success of the pattern branching TMDs with MCR and IO, which can describe the dry EM production over a wide range, and it could be a proper prediction of low PT spectrum, which is needed for the WMAS determination. And I think that's all. Thank you for your attention.
Thanks a lot for this very nice talk. So we have a question by Wenchen. Please go ahead.
Yes. In one of the slides, you say you actually construct your things using the X feature. So the first question is, do you include this like a new C A66 the QT data in your fitting? Here you say you include data points. So are all of this data you show in the fixed target, are they already inside your database for your X feature fitting?
I don't know it by heart. Maybe Hannes or Saha, could you comment on it? But from my remember, I don't think so. I think only HERA data.
Just a comment. In the fit, it's only HERA data, the high energy HERA data. So no new C trillion data were included in the fit.
So how can this PT information, so how in this low PT, how in principle for this TMD, people need to get some kind of a PT spectra as an input in order to really get it, because all of this is non-perturbative effect. So I'm curious how this non-perturbative effect is described in your framework, how you obtain this information. it cannot be simply come from QCD evolution effect.
No, there's one piece which comes from the intrinsic KT distribution, which is parametrized, but everything else is coming from the perturbative evolution.
Mm-hmm.
So the intrinsic KT is a Gauss distribution with a width of 500 MeV, which we determined for the high energy LHC measurement, and then the same thing is used to describe the low energy data.
Yeah. Sorry, second quick question is, can you apply your framework for calculate the angle distribution for Drell-Yan?
I guess so, yes.
Thank you.
And this is Ilya Gorbanov. Can I ask one more question?
Yes. Yeah, okay. Go ahead.
Chenya, I see you. You nicely describe the CMS PT spectrum, ZPT spectrum on slide number 8. But did you consider using, for those measurements, there are also measurements of the phi star available. Phi star is essentially the PT distribution, but with a lower, with better resolution available. Did you consider using, studying the phi distribution?
Yes, thank you. And actually the phi star is also included in the paper. So, I mean, so we also could produce a phi star. And I do not remember if we compared the predictions with the CMS data yet.
I think it's even in the CMS paper, if I start comparison.
Okay, thanks again. Very nice talk. If there are no further questions, we'll move to the next speaker, Marco Marconde. We'll talk about the area measurements by compass. Okay, see your slide.
Perfect. Hi, so this is Marco speaking. I'm giving a talk today about the Drell-Yan measurement at Compass on behalf of the collaboration. So the outline of this talk is presented here. I will quickly go through the experimental setup before discussing the results, namely polarized Drell-Yan, unpolarized Drell-Yan, and double jet side production. So the experiment was earlier presented by Polulini, so I will quickly go through the Drell-Yan specificities only. However, Compass is a two-stage spectrometer of 60 meter long. The picture is bottom right. In 2015 and 18, Compass used Hadron beam made of 97% negatively charged pion to measure Drell-Yan. And this setup has two main hardware features, namely the polarized target and the Hadron absorber. So that's what we are going to see in the next slide very quickly. So first, the dilution refrigerator is capable of cooling down the polarized target to few millikelvin. The targets are in the picture bottom left in yellow. There are two targets, and they are made of a mixture between solid NH3 bits in a liquid helium bath. This low temperature is used in order to keep the high polarization of the proton spin to about 70% to study transversely polarized asymmetry. So on the other hand, on the right-hand side picture, you have the absorber in purple. It is an alumina structure with a tungsten core positioned downstream of the polarized target. Moreover, it contains two active materials, aluminum and tungsten, used as targets for physics analysis. In the past, COMPAS measured non-zero asymmetries of the spin structure of the nucleon using the Silis channel. And today, the purpose is to measure the same asymmetries using the same apparatus, but through the Dralian process. Thanks to symmetries between those processes, time symmetry, the idea is to verify fundamental features of the TMD PDF factorization in QCD. And so the Dralian process is on the right-hand side picture. It's a time-like process involving two hadrons in the initial state here. And it has the advantage compared to GIS to be a clean electromagnetic process and not involve fragmentation function. Here, as we have two hadrons, one is coming from the target and the second one from the pion. And we can, of course, probe a wide range for the negatively charged pion PDF. So due to the correlation between Dralian and Silis and the time-odd nature of the previously quoted non-zero asymmetry, one expects in the theory sign change, and that's what we are aiming to claim here. Additionally, there is, using the same apparatus, an overlapping region in X and Q square. So we aim to have minimization of Q square evolution effect here. So at COMPAS, the kinematical coverage can be divided here for this talk into two parts. First, Charmonia mass range. On the other hand, high mass range. Here in the picture, bottom left, which is showing the mass spectrum of the diamond. So in the sketch, the hadronic interaction is shown in the target rest frame, and the phi Sievers, phi S, is the angle between the transverse component of the spin and the QT. Again, bottom right, you see a plot which is the Bjorken of the pion and the Bjorken of the target. And as I mentioned before, we have a quite wide range to probe that would help also understanding the pion PDF. So at leading twist, the spin nucleon structure is parameterized by 8 twisted 2 TMD PDF. On the picture on the right-hand side for this talk, the main contributor are transversely nucleon spin polarization, more precisely the non-zero amplitude function, Sievers for unpolarized quark. And the single spin Dralian cross-section is defined here in the slide. And expected to be proportional to amplitude coefficient that are shown in the bottom of the slide. So those amplitudes are a convolution of the TMD PDF and split it into 3 parts. First, unpolarized asymmetry, which is still ongoing analysis at COMPAS. This will help also to understand the non-perturbative, the Lamtung relation, and might provide some input about this. On the other hand, you have also transverse asymmetry, namely Sievers velocity and transversity function, and also subleading twist amplitude. So now switching to the first results. The results of the amplitude is assuming sign change here and gives the following results. So the different amplitudes are on the left, and for the Sievers, we can see good compatibility between 2015 and 2018 results. So they are about point to point about 0.7 times the systematics are about 0.7 times the statistical uncertainty, and are indicated in the plots by color bands. I also wanted to highlight the Sievers asymmetry here, which is non-zero, and assuming sign change, you have here in red the data points published by COMPAS, compared with 3 different theoretical approach which assume sign change for Sievers function. These results are preliminary for 2018, and actually it's only 50% of the total statistics. So in the end, I wanted to highlight also in the bottom right plot the different asymmetries. So the first one, Sievers, which shows a positive sign below above 0, about 1 sigma. That will help understanding sign change. The second one, which is non-zero below 0, above 2 sigma, and that would help understanding the universality of nucleon transversity function. Third one, the Price velocity, which is near 0, and the two last subleading twists, which are also compatible with 0, and this is kind of expected because of the subleading nature. I would like now to switch to unpolarized results. And so the unpolarized studies are currently in full swing, and we aim in the future to publish absolute cross-section on different targets. At this time, we have projection of statistical uncertainty, mainly on NH3 and also tungsten. In this picture, you see the results of the projection for COMPASS, the projected statistical uncertainty for 2 bin in mass using tungsten targets. This is compared with the results from also E615 and DYN-NLO simulation at NLO. And we aim in the future to have better systematic uncertainty compared to past experiments, meaning below 10%. Still in the scope of unpolarized Drellian and JEPSI, the age dependence results are also expected in the near future. As we collected results on 3 different targets, we expect to provide those results soon. And currently, the statistical projections are shown for the ratio between tungsten and NH3 on the right-hand side picture as a function of the X-Bjorken target. These results in black points are a combination of 2015 and 18 data from COMPASS and compare with different results from MA10 that was an experience in the past doing some similar measurements. So following the ePPS extraction of the PDF, we could contribute in the future to modification of the proton-free PDF induced by the nuclear corrective factor here, as shown in the formula. This will help to contribute to the understanding of non-perturbative effects, as well as correlation with QT and underlying JEPSI process. So I also wanted to show you here a picture of the Hermes wall data and the sensitivity of the COMPASS apparatus in the corresponding range for Drellian in that case, as compared to Hermes in DIS. So along the line of the JEPSI, I would like now to just finish this talk and discuss a few results about the double JEPSI production that was studied at COMPASS very recently. So the double JEPSI production, long story short, can be obtained from 3 different ways, either intrinsic charm process, single parton scattering, and double parton scattering. The measurement was first done by NA3 experiment, which was also using a negatively charged ion, which was also a fixed target experiment. However, the published results was the results were published without acceptance correction, which makes the interpretation more complex. So here at COMPASS, we studied the double JEPSI production, and the measurement of the cross-section of double JEPSI production is shown on the right-hand side, the ratio first between STS and DPS, but also the cross-section results for the 3 different targets. The systematics are about 25% here, but comparable with the statistics. And these results can be compared with directly NA3 results. In the case of the COMPASS data, the COMPASS data are well describing the SPS and intrinsic charm model. SPS appeared to be, as shown on the bottom right plot, appeared to be a dominant mechanism here, while DPS is expected to be strongly suppressed at fixed target energy. So finally, to summarize, here at COMPASS, we measure 2 years of data taking, and half of the statistics for 2015 remains to be published. soon. I introduce you also, I show you some results about the single spin asymmetries and the ongoing analysis for unpolarized Drollian. Ending with this double jet side production. So thank you for your attention.
Thanks a lot for this nice presentation. Is there any question to Marco? Hannes, please go ahead.
Yes, I have a question on the unpolarized Drollian studies. Do you plan also to have a PT distribution of unpolarized Drollians at some stage? So just in light of the talk from Chung before, it would be interesting.
Yes, exactly. Yes, I think that Compass can contribute quite a lot here. In some sense, a goal would be to publish the correlation between X-Feynman and PT, as well as root square of tau and PT. Yeah.
And this would be great. Thanks a lot.
Okay, David.
Yes, can you hear me?
Yes.
Yeah.
Yeah.
Good. I was wondering this conclusion in your summary that intrinsic charm is negligible. If you go back to slide 12, your red line has both, no, SPS and intrinsic charm. So why do you say that the data does not support intrinsic charm? I mean, with these statistical uncertainties, you cannot tell, no? Can you?
Correct. Yes, I was indeed comparing SPS and intrinsic charm model here in red. However, the intrinsic charm contribution in blue here is quite low. So I wanted to highlight that, right, a single parton of scattering is here the main contributor here. But it remains compatible within error bar.
Okay.
Okay. Is there any other question to Marco? Otherwise, we move to the next speaker, Jennifer Roloff, who's now switched subjects to so measurement of jet substructure and jet fragmentations in the Atlas detector. Okay.
Great.
I see the slides whenever we're ready. Thanks.
Okay, very good. Yep, so today I'm going to be talking about measurements of jet substructure and jet fragmentation with ATLAS. So before I dive into the measurements, I think it's useful to take a moment to talk about why we're interested in doing these measurements. So first off, jet substructure provides an insight into QCD across multiple scales. So you can, in a single measurement, understand everything from your fixed order effects to your parton showers to your hadronization. In addition, I mean, at the LHC, we use jets in many of our analyses. And for these, we require Monte Carlo generators to model our jets. And this is the dominant source of uncertainties for a lot of analyses. And in particular, our modeling of gluons is particularly poor. So if you have a better understanding of jet formation, if we have more measurements of QCD at these different scales, this can go into providing better models of jets and better tuning of the different models that are available. And then finally, if we do understand jets better, of course, this can also lead to better observables for our tagging, which is relevant for everything from quark gluon tagging to W and top tagging, as well as Higgs tagging. So the first measurement I want to talk about today is a measurement of jet fragmentation. So jet fragmentation is kind of the first types of substructure measurements that have been done. They've been done for many years now. Essentially what these look at is looking at the distribution of particles within a jet. So there are many different types of observables you can measure. This includes the number of charged particles or the number of particles, the radial profile, and many more things. These aren't calculable, but their energy dependence is calculable with perturbation theory. And these are important inputs to tuning Monte Carlo. And you can see in the plot here of the average number of charged particles as a function of the jet PT, you can see that there's some significant disagreements between data and Monte Carlo, motivating measurements like this to help with the tuning. The measurement that was done recently at 13 TeV on ATLAS This was done using tracks within a jet, so charged particles. This is because it gives very precise measurements of the substructure of a jet. And one interesting thing to note is that the jet fragmentation doesn't depend strongly on eta, just on the initiating parton. So if you have a gluon initiated jet, it looks, about the same if you have it produced very centrally or very forward. But the fraction of gluon or quark jets changes as a function of eta because of the parton distribution functions. So you can see in the plot on the right, the fraction of jets which are initiated by gluons. So you can see that more central jets tend to be more gluon dominated than the forward jets. Since quark and gluon jets look a little bit different, this results in different distributions of these jet fragmentation functions as a function of eta. So you can see in the bottom a plot of the average number of charged particles for more forward and more central jets. And you can see that, as you might expect, the more central jets, which are the more gluon-like ones, have more charged particles because gluons tend to radiate more. So this is one handle on understanding the behavior of gluon jets, which, as I mentioned before, is very important for our understanding of the modeling of jets. But you can go one step further, actually, and you can actually extract the underlying quark and gluon distributions. So like I said, since the actual fragmentation doesn't depend on the eta region that you're in, it only depends on the initiating parton. You can imagine that these distributions are a linear combination of the quark and gluon distributions multiplied by the fraction of quark and gluons. So if you look at the number of charged particles distribution, it should be the quark distribution times the quark fraction plus the gluon distribution times the gluon fraction. So this is simply a linear equation, and you can invert this if you have two measurements in different eta regions with different quark and gluon fractions. And so you can do this inversion to produce your quark and gluon distributions determined by a Monte Carlo generator where you get the quark and gluon fractions from, for example, Pythia. In addition, I can't talk about this too much here, but one other possibility for doing this is using topic modeling, which extracts the distributions using some sort of minimization process. And essentially, it doesn't require any sort of model input into the quark and gluon fractions. And so it's able to do this in a much more model independent way. And you can see the results of this on the next slide, where you can see the extracted quark and gluon distributions, as well as the kind of underlying quark and gluon distributions as given by the Pythia labels. And you can see that both of these methods provide very similar results for the extracted quark and gluon distributions and look very nice. So this is the first time we've used topic modeling in a measurement, which is, I think, a very exciting way forward to produce more model independent ways of extracting this information. So on to the next topic. One interesting thing about substructure observables is that in general, they're not typically calculable. So this is because you have contributions from non-global logarithms, which make it very difficult to produce accurate calculations. But there is a type of grooming algorithm where grooming algorithms remove soft and wide angle radiation from a jet. Soft drop in particular does this in a very theoretically nice way. So it removes any contributions from these non-global logarithms, meaning that you're actually able to produce accurate calculations beyond leading logarithmic accuracy. And so we did a measurement of the soft drop jet mass in dijet events. We actually measured the relative jet mass instead of the mass directly, because this reduces your dependence on the PT of the jet. For quark and gluon jets, your mass scales with PT since you have more radiation. And in addition, we used a logarithmic scale for in order to get better access to what's called the resummation region, where these non-global logarithms would have been relevant, and instead you have the logarithms that are dominant. So we're measuring rho, which is log of m squared over pt squared. And you can see an example here of the measurement of the jet mass compared to 3 different calculations. So an NNLL, an NLO plus NLL, and an LO plus NNLL. And it's interesting to look at this. There's some interesting features that you can note. So you can divide this into 3 different regions, the non-perturbative region, the resummation region, and the fixed order region. In the non-perturbative region, the analytical predictions do not agree very well with your data, but they're also not designed to work very well here. This is not where you would expect them to behave properly. In the resummation region, this is where the logarithm is coming into play. And you can see that there's very good agreement between all of the analytical predictions and the unfolded data. Then finally, in the fixed order region, you can see that, for instance, the NLO plus NLL prediction agrees much better than the LO plus NNLO prediction. This is because the fixed order effects are very important here. So obviously the NLO is going to provide a better understanding of this region. You can do a similar trick here where you extract the quark and the gluon distributions for these as well. This is done using the plot I'm showing here is done using a track-based measurement instead of the calorimeter-based measurement. So this can't be compared to calculations, but it does provide a much better precision for the jet mass. And one interesting thing about the jet mass in particular is that in the resummation region, so in this kind of middle mass region, the slope of this distribution is proportional to alpha S times the color factor. So as you would expect, the gluon slope is larger than the quark slope because it has a larger color factor. And you can kind of see a nice, nice little slope here that, is related to alpha S. This is currently done using the linear extraction. So there is some model dependence in this based on the quark and gluon labels from Pythia. And the dominant uncertainty is the jet modeling as well. So finally, I want to talk about one final measurement that we did of the Lund jet plane. And so this is a fairly new idea for an observable. The measurement came out earlier this year. So you can imagine a jet as an approximation as a series of soft emissions around a hard core, where the hard core represents your originating quark or gluon. And you can characterize these emissions. There's a couple of ways you can characterize them, but one way you can do this is using Z, which is the relative momentum of the emission with respect to the jet core, and delta R, which is the angle of emissions with relative to the jet core. And the reason that this is very nice is that this factorizes different effects into different regions of this two-dimensional plane. So just like the jet mass, where you had these three different regions, you have a similar sort of effect for the Lund plane. The reason the jet mass exhibited some of the same behavior is because it's actually just a line in this plane. So what happens if we measure the whole thing? So we measured the two-dimensional Lund jet plane in dijet events, again, using tracks in order to have a higher precision, and unfolded to the charged particle level here. There's a lot of physics information in this picture, but it's too much to get into in a short talk here. So instead, what can be useful is to look at a single slice of this. So for instance, if we take a slice in Z and we look at this, we can actually see the uncertainties and the comparison to different Monte Carlo generators. So here you can see a comparison to 6 different Monte Carlo generators. And these 6 were chosen with a reason. So the Pauheg and the Pythia, these have the different, fixed order calculation, but the rest of it is the same. For the Sherpa, this has different hadronization models. So, but everything else is the same. So the parton shower and the fixed order calculation is the same. And then finally, for the Herwig, you have 2 different parton showers. The hadronization and the fixed order is the same, but the parton shower should look different. So you can neatly see this factorization here. So in the wide angle region, where you have the hard and wide angle emissions, you expect the parton shower effects to be really dominant, and this is exactly what we see. Whereas when you move to the more hard collinear region, where you expect the non-perturbative effects to be large, such as hadronization, you see large differences between the 2 different Sherpa models, and very small differences between the other Monte Carlos. And so this nicely demonstrates the power of this factorization in being able to understand our jets. So just to sum up, jet substructure measurements are a really powerful tool for understanding QCD across multiple scales. We can now do, we now have comparisons of measurements and theoretical predictions for certain substructure observables based on advances in different grooming algorithms. And one powerful thing about a lot of these is the separation of different physical effects. into different regions of a measurement. So you can actually see where different parts of QCD are coming into play within a single measurement. And these measurements are going to be really important moving forward in understanding the behavior of gluons much better, which is going to be important to help us move towards precision for the HLHC. And things such as topic modeling will help to allow for more model-independent extractions of this behavior. Thanks.
Okay, thanks a lot. Very nice presentation, measurements. David, I see your hand raised. Is it? Do you have a question, or we just kept from the last one?
Yes,
Okay,
I have
go
a
ahead.
question.
Okay,
Nice talk. Can you please go back to slide 17? What is the POHEC plus Pythia here? Where does it show? I cannot read it off. I mean, you said that these have the different, the same order in fixed order accuracy, but that's not true. No, POHEC it's NLO. Whereas Sherpa and Herwig are.
No, I said they have
no?
different fixed order calculations.
Sorry. Okay.
Yeah.
So what is the POHEC here?
It lies right on top of the Pythia, actually. So you can see, for instance, here you can see that they are slightly different. But this is part of the factorization effect that I was talking about, where the fixed order calculation shouldn't be very important in either of these two regions, and so you don't see large differences between the Pythia and the POHEC plus Pythia, which is exactly what you'd expect based on how this plane is divided.
Mm-hmm. Okay, thank you.
Okay, thanks. So we have time for another question. Ilya?
Hello, this is Ilya Gorbanov. I have a question regarding gluon identification, quark gluon discrimination. Are you aware of the ROC curves for gluon identification, and can you compare those ones for Atlas and CMS who have better working points available, and if you know the ways to improve the discrimination power?
So yeah, I guess the measurements we're doing here aren't directly trying to improve our quark gluon taggers, but I think a lot of this stuff will help reduce our uncertainties on these, which are quite large because our gluon modeling is very bad. And so by getting better models of our gluons, it will help make these taggers a lot better for both Atlas and CMS.
Thank you.
Okay, thanks again to Jennifer. If there's no other question, we move to the next speaker. So Denise Sunasasi will talk about jet substructure and boosted jet measurements at CMS. Okay, I see your slide.
Okay.
Please start whenever you're ready. Thank you.
Thank you very much, Antonio. Hello, everyone. I'm Deniz Sunarçerçi. I'm going to talk about the jet substructure and boosted jet measurements at CMS on behalf of the CMS collaboration. Okay, let me just give you kind of a reminder about the main goal of the QCD studies, that is to improve our detailed description of the standard model physics. And as we all know that the QCD is the theory of strong interactions describing the interactions between the quarks and the gluons. And since the experimental signature of quarks and gluons, which are the jets, they are abundantly produced at the LHC. And one can easily say that LHC is a kind of a jet factory. So it is very important to have a look at the solid and insightful description of jets, and their substructure relies on the deep understanding of the dynamics of strong interactions in collider experiments like LHC. Better knowledge of jets substructure will help to improve precision measurements involving jets beyond standard model searches with boosted objects, flavor tagging, as well as pileup identification. The most commonly used JET algorithms are actually the cone algorithms as well as the sequential algorithms. In the sequential JET clustering algorithms, which is based on the concept of the jets are the product of the successive parton branchings. And in this algorithm, it is defined with interparticle distance, which is denoted here with the ij, and the beam distance with the ib. Here is one free parameter, which is called P, and the behavior is controlled with this parameter. And it can have these three values according to the algorithms. Here you can see that there are two figures are shown in here. Jets are obtained on the left-hand side with the Cambridge-Aachen algorithm when the radius is equal to 1. On the right-hand side, the jets are obtained with the anti-KT algorithm. The shaded regions here correspond to the catchment area of each jet, and I just would like to emphasize that typical choice for the within the CMS for the jets are the cone size is 0.4, or in some analysis 0.8 is used. For the jets with substructure, typically it's called grooming. In these algorithms, which are used to remove the soft contributions, and especially the large angle soft radiation of the jet and underlying activities, and to focus on the hard structure of the jet. Grooming makes comparison easier with theoretical calculation, though we can remove the large logarithms by using this. For the modified mass drop tagger, which is a kind of a tool to isolate the boosted Higgs bosons decaying into BB bar pairs, and from the QCD background by using the condition given with this item. So there are various experimental jet substructure observables, such as I picked up a couple of them here, and I'm going to focus the shared momentum fraction, which is also kind of a observable that can, if it has a value of 0.5, one can identify two hard subjects, and if it has a smaller value, as you can see, one hard subject can be identified. And there are some other jet substructure observables like hard splitting, opening angle, RG, and groom jet radius. And one another is the groom jet mass. This observable depends on opening angle, and when it has a small mass, there are collimated jets having with few constituents inside. When it has a larger mass, we have a broader jet having with many constituents inside. For the soft drop grooming, the goal is to find two hardest substructures inside the jet. So here, as you can see, the jets are measured with anti-KT algorithm, and it is reconstructed with anti-KT jet algorithm. And then reclustered is done with the Cambridge-Aachen scheme to create a pairwise tree of subjects. Then if it fails this condition, the soft, which is called soft drop condition, as you can see here, if it fails, it is removed from the algorithm, from the process, and then the process continues until the branching passes. And when this CA finishes, the cluster iteratively starting from the last step. On the right-hand side of this slide, the kinematic diagram in terms of two variables, Z-cut and the R0 are shown here. As you can see, this is the area for the soft drop when the beta is above the 0, and when it has a beta equal to 0 is this is the collinear area, and this is the beta less than 0. This is the area. So the main interest in the soft drop part here. Okay, let me come to the measurements that we have performed with the CMS detector. This is the measurement of the differential jet cross-section, which are determined as a function of the ungroomed and the groomed jets, jet mass in die jet events. and in bins of PT. This is the PT region I have picked up in here for the 2-1. On the left-hand side, you see the ungroomed jet mass, and the right-hand side, the groomed jet mass mg as a function of the differential cross-section. What we can see in here is the higher systematical uncertainties observed for the ungroomed rather than the groomed jets. And when we look at the grooming algorithm, we clearly see that this grooming algorithm considerably lowers the jet mass and suppresses the Stakov peak. In this measurement improves the precision by removing contamination from the soap particles and the pile-up events. For the normalized cross-sections, which is shown also for the ungroup on the left-hand side and the groomed jet mass, for the all PT bins starting from 200 and above 1300 GeV, just for a clear or better visualization, the data points are multiplied with a scale factor here. For generally speaking, the theoretical predictions agree with measured cross-sections within the uncertainties for masses from 10% to 30% of the transverse momentum of the jet. Okay, so as we are interested in the jet substructure and why don't we have a look at the TT bar events? Because we know that the top quark pair events are abundantly produced at the LHC, and it is a very good probe for jet substructure measurements, since they have very rich final states having light quarks, weak quarks, gluon with high PT, boosted W and top. And such kind of events also has high purity and relatively orthogonal event selection criteria. In the following slides, the lepton plus jets event samples as used in the measurements. Okay, this is one of the measurements that we have published. Actually, we have made various, in this publication, various observables measured, listed in here. And the all jet substructure observables have been measured not only for inclusive jets, but also for bottom quarks and for samples enriched with light quarks and gluon jets. On the right-hand side of the slide, the distribution of charge multiplicity relevant for the quark-gluon discrimination is shown for those 4 jet flavors in here. In this second panel, this panel shows the corresponding ratios of the different flavors over the inclusive jets data. And at the bottom of the plot, 3 sub-panels show the ratios of the different Monte Carlo predictions over the jet flavors. And differences between the quark and gluon enriched samples do not seem to be very strong. For the results were compared to the various generators, POHEC plus PTA8, POHEC plus Herbig 7, and also PP8 with final state radiation up and final state radiation down were also checked. And the Sherpa 2 and the Dyer 2 was the prediction that have been used in this measurement. This is the actually unfolded distributions are shown here for the charge and the charge neutral particles for all jet samples. I just show here the charge ones. For the more information, you may have a look at inside the paper here. I would like to emphasize that the distribution of the groomed momentum fraction, which is ZG distribution, is presented first time in here in this paper. And there's a good data model agreement in this observable only for the Herbig 7. However, there's a large spread in generator predictions when we look at the other predictions. And when we look at the angle between groomed subjects, delta RG, we see a strong dependency on the amount of the final state radiation. We have also made a recent publication. This publication is related with the running of top quark mass, which is experimentally investigated for the first time. And the aim was following. So we have measured the top quark mass as a function of the scale MTT bar. And we have performed the precise measurement of the differential TT bar cross-section as a function of the TT bar mass. And the running was extracted by comparing to differential theory predictions in minimal subtraction renormalization scheme. Measured cross-sections and their uncertainties are compared to NLO predictions in this scheme as well. As I said, the reference renormalization scale factor is taken as the top mass, and here three different values of the top mass, starting from 162 GeV to up to 166 GeV were used. So I should also say that this data was unfolded to the parton level. For the running of the, in order to extract the running in TT bar, which is defined as a ratio of the top quark mass to the reference mass of the top quark mass. So this is the definition given by the theory, and this is the experimental definition that we have used. What we can see here that the theoretical side, the running depends only on the RGE, but for the experimental side, we can get benefit from cancellation of the correlated uncertainties. Here, the initial scale was chosen as a 476 GeV. So the upper plot shows the extracted running of top quark mass compared to one loop RG precision, which this is evolved from this mu ref. This is the initial scale that is written here. And on the bottom, this result is compared to the value of the MT extracted at the NLO from the inclusive TT bar differential cross-section. And we can see that there's a good agreement between the with the RG on a wide range of scales up to 1 TeV. Another analysis, which is a very fresh one actually, this is the differential TT bar cross sections. We have measured the high PT top quark pairs, the production cross section for high PT top quark pairs. So in this analysis, events where either both top quark candidates decay hadronically, and one of the top quarks decay to a B-jet, leptonically to a B-jet are used. So the substructure observable used extensively for the tagging of the top quark, and this is the N-jet subunit variables that are measured and available in the physics analysis paper. On the right-hand side of the slide, you see the absolute cross-sections, differential cross-section, and on the bottom of the slide, the normalized cross-section is given, and the data is compared with POVEC plus PTA8 and Monte Carlo et al. Together with PTA8, and POVEC plus RORIC plus is also one of the predictions used to compare the data, and both data unfolded to particle level. So hard radiation centers found with exclusive KT algorithm. We have applied this grooming technique in order to remove soft and wide angle radiation from the jet, just to improve the mass resolution. And as you can see, it really helps to improve the mass of the, to measure the mass of the top quark. So this brings me to the summary. So there is a significant ongoing effort to improve our understanding of QCD with jet substructure measurements. And this kind of measurements can give a light on the standard model in extreme phase space region. Both inclusive and differential cross-section measurements performed by the CMS collaboration, and this can tackle different modeling aspects at different phase space region. Changing from the low PT to high PT, various interesting measurements allow us to see the strengths of different Monte Carlo too. So some of the Monte Carlos needs fine tuning. Of course, we are not done yet, and there are still more measurements and efforts are ongoing. And please stay tuned. And thank you for your attention.
Thanks a lot, Denise. That's very nice presentation results. So I have time for one quick question.
Thank you.
So I don't see any hands raised. So I think it was all very clear. So we can move now then to the last contribution in this session by Anthony Badea. Anthony, are you there?
Yeah, can you hear me?
Yes, yes. Could you try to share your slides?
Yeah, I'll share right now.
Okay.
Can you see them?
Yeah, I can see them. So Anthony will talk about multi-differential and unbeam measurements of hadronic event shapes in E plus and minus collisions at 91 GeV from Aleph using open data. So please go ahead whenever you're ready.
Fantastic. So, hey everybody, my name is Anthony Badea, and I'm a graduate student at Harvard University. And today I'll be showing preliminary results on the use of a new multi-differential and unbend unfolding technique known as omnifold, applied to archived LUP1 data from the Aleph collaboration. And I'm presenting this work on behalf of Patrick Kaminsky, Eric Matayev, Ben Nachman, Yenji Lee, Jesse Thaler, Austin Batty, and Chris McGinn. And before I start, I want to thank the organizing committee for the ICHEP conference for adjusting to the circumstances and helping us all stay connected from our homes. And thanks everybody for making the best out of the situation. And since this talk is only supposed to be around 10, 12 minutes long, I'm going to be quite brief in some of my explanations and where possible, focus on exciting ideas rather than exact details. But of course, if there's anything you have questions about, please reach out to me or any of my collaborators with any questions or comments. And throughout this talk, I'll cover three main topics. First is unfolding, data, and physics. I'll begin by describing what we view as the current challenges facing traditional unfolding methods and offer an overview of the new technique deployed. Then I'll give a quick overview of the Aleph archive data. And after this, we'll touch on the physics we're interested in, namely 1 minus thrust and log 1 minus thrust. And I'll show our preliminary results. And finally, I'll wrap up with a summary, a few comments, and provide my contact info. Moving on to slide 3. As I said, we think that the current traditional unfolding techniques face several challenges, as outlined in this slide by one of my collaborators, Patrick. First, these methods, such as iterative Bayesian unfolding, are inherently binned. This means that the binning is fixed ahead of time and cannot be changed later, and the unfolding performance is highly sensitive to the binning. Second, the methods are only practically useful for a limited number of observables, since the binning of each individual one induces a large computational complexity. Third, the unfolding or response matrix typically depends on an auxiliary feature, i.e. that the detector level quantity may not capture the full detector effect. An example of such a feature can be seen in the case of two jets acquiring the same mass in different ways, as shown in the bottom left of this slide. Though the jet's mass is the same to the unfolding algorithm, the detector effect could be quite different. Another example of these challenges is a recent, very nice and interesting loon plane measurement by the Alice collaboration, which was shown, I think, 2 talks ago. And this measurement was extremely interesting, extremely nice. It's something that was brought up at Boost, was that the axes that were chosen weren't exactly what the theory paper used to compare with. And if the collaboration wished to change the binning or add in another observable to change the axes, they would need to redo in the unfolding, which would likely drastically increase the computational complexity and have to go through another procedure to be published. Now on slide 4, these challenges were the primary motivation behind Omnifold. And for the sake of time, I'm not going to go into the details of the technique, but you can find links to other talks and an example Jupyter notebook in my backup slides. But in a nutshell, omnifold is a multi-differential and unbinned machine learning-based generalization of iterative Bayesian unfolding, or IBU. And for those of you familiar with IBU, the key insight going from IBU to omnifold is the following. First, the unfolding matrix is accessible via the likelihood ratios of data, reconstruction, and truth. Second, the likelihood ratio is the optimal binary classifier according to the Neiman-Pearson lemma. And third, if you assume a softmax activation, then the likelihood ratios can be accessed by training a network to classify events as either data or reconstruction, and either reconstruction or truth. So as I said, there's more details in the backup slides. And if you want to see the original paper, please check out the publication by my collaborators. Moving on to slide 5. Up until now, omnifold has only been applied to Monte Carlo, but thanks in large part to the ALF collaboration, we're able to deploy the technique on real collider data. So data that were used was collected at LEP at 91 GeV, and for this analysis, we are using approximately 1.36 million events. We use the event and track selections supplied by the collaboration, which are detailed in the backup slides. And the unfolding also utilized archived Pythia 6.1 with matched reconstruction events, which were also supplied by the ALF collaboration. And in particular, we want to thank Marcello Maggi and Gunther Dissatori for their foresight in preserving the data, which is now enabling us and others to expose different aspects of it in ways that were not known in the 1990s, and for helping us work with the data today. Personally, I hope that in the future, people like us will be able to do the same thing with LHC data. And for this data set, myself, Yenji, and others not involved in this specific analysis have already published a measurement of the two-particle correlation function that you can check out if you want to read more about the data, or if you want to read more about progress in small system collectivity and heavy ion physics. Now on slide 6. So we're currently working on the measurements of 1- thrust, referred to as tau, and log tau. And briefly, the thrust axis is the axis that is most in line with the momentum of the particles in an event. And the thrust value is the normalized projection of the momenta along that axis. Tau, which is 1- thrust, goes between 0 and 0.5, with 0 being a perfectly back-to-back event and 0.5 a perfectly uniform event. We're interested in these observables because there's a large discrepancy between theory and experiment in the highly perturbative regions of phase space, which correspond to low thrust or high tau, as well as in the non-perturbative regions. And we chose to focus on tau because most modern theoretical calculations work with tau to better highlight the nuclear physics, resummation, and fixed order regions. And very briefly, the reason we worked in both linear and log space is because these spaces highlight different physics. Together, they provide insight into the perturbative and non-perturbative physics in play and particle collisions. And an example of this is the measurement of the soft drop jet observables in PP collisions to the right by the ATLAS collaboration, which coincidentally was also shown, I think, in the same talk as one of the earlier plots I showed. And this is an extremely nice and interesting measurement. And by conducting the measurements in both linear and log space, the collaboration exposed the contributions from non-perturbative and perturbative physics. Now, moving on to slide 7 for the 1- thrust result, or tau. In the top panel, the black line is the not unfolded Aleph raw archive data. The orange is the Pythia 6.1 reconstruction. The dashed blue is the truth level archive Pythia 6.1. The green is the Aleph collaboration's measurement. The gray is the unfolded distribution with IBU, and the red is the unfolded distribution using unifold, which is omnifold one-dimensional variant. And in the bottom panel, the ratio of the above distribution to the generation level distribution is shown. And the green bands around the Aleph measurement are the uncertainties that are provided by the collaboration on hepdata.net, which is also where we got their exact data points. And if you're looking in both plots, notice in the regime where the Monte Carlo accurately models the physics, unifold performs similarly well to IBU and is within the uncertainty supplied by the ALF collaboration for the entire phase space. As this is only a preliminary result, there are more details that we're working through at the moment, but this already gives us confidence that the method is performing as expected, and further results will be available in the future. Moving on to slide 8 for the log tau result, we once again have the same color coding as the previous slides, and the bottom panel ratios are also with respect to the gen level distribution. We can see that working in log space spreads out the nuclear physics region or the non-perturbative region over more bins and compresses the perturbative regions, so the issues in Pythia are better highlighted. For large values of tau or small negative values of log tau, Pythia is missing fixed order corrections. Whereas for small values of tau or large negative values of log tau, the non-perturbative model in Pythia hasn't yet been tuned to data in the very low log tau region. This is shown on either ends of the unfolded distribution where the ratio to gen is significantly away from 1. With modern Monte Carlo generators, we expect to get better agreement in the large tau region, but in the small tau regions, it's not clear because the discrepancy arises from a tuning issue, no matter which generator you use. In the future, we're going to use different generators and try out different combinations to see what the different effects are, and we'll report the findings in the paper that's to come. And to wrap up, my collaborators and I are in the process of deploying a new, highly promising unfolding technique on real E+ E- data to measure tau and log tau. The current and previous results suggest that Omnifold is a viable solution to the challenges facing modern unfolding techniques. And as I've shown, significant progress has already been made in deploying Omnifold or Unifold on real collider data via the ALIF archive data. And going forward, we're working on handling uncertainties, comparing the results with different Monte Carlo generators, and ultimately performing a multi-differential unfolded measurement. Lastly, before I go, I want to say thank you again to the ICHEP organizers, all the participants, and those of you watching this talk on behalf of my collaborators. I hope that everyone's safe and well and still having some fun, and it's great to stay connected. And if anybody has any questions or comments, my email is there at the bottom, and please reach out to myself or any of the collaborators. Thank you.
Thanks a lot. Very interesting and nice talk. I see Marek. Go ahead.
Yes, this was fascinating, Anthony. In the example you discussed, you focused on shape variables. Mm-hmm. Are there any thoughts of using this approach for BSM physics?
I know that from some of my other collaborators, they're thinking about this right now. For testing it with the ALIF archive data, we're currently focusing on these event shape variables because the other details of the technique still need to be hashed out a bit more. But I think in the future, definitely trying to use it for BSM physics is for sure an option.
For example, you have Mike Williams in MIT, and who is a part of LHCb, and LHCb has all these fascinating data about possible lepton flavor violation, and I wonder what you could do for them.
Yeah, I definitely agree, and I know I was at MIT as an undergrad, and Yenji and Jesse, I don't know exactly, but I'm sure they're in contact with Mike about something regarding that. I'm pretty sure Jesse is.
Right. So that would be very interesting. Thank you.
Yeah, I'm taking a note of that. Thanks for the comment.
Okay, thanks a lot. Is there any other question to Anthony? If not, thanks again to Anthony and all the speakers in this session. So this is the end for today. And we'll reconvene tomorrow 8 a.m. Europe time. Thanks to everyone. Have a nice day.